Understanding time series forecasting. Time series forecasting is a specialized area of data analysis and machine learning focused on predicting future values of a variable based on its past observations. Unlike other statistical or machine learning tasks that assume independence between data points, time series data inherently possesses a temporal order, meaning the sequence of observations is crucial and carries significant information. What is a time series? A time series is a sequence of data points indexed or listed in time order. Most commonly, a time series is a sequence taken at successive equally spaced points in time. Examples include daily stock prices, hourly temperature readings, monthly sales figures, or yearly population counts. The defining characteristic is that each data point is associated with a specific timestamp. Consider a simple example, tracking the daily closing price of a particular stock. Each day, we record a single value, and these values, when ordered by date, form a time series. Let's illustrate this with a simple synthetic time series using Python. We'll generate a series representing daily temperature over a month. Download the code on OnePageCode Substack. We begin by importing the necessary libraries: code snippet for data manipulation, code snippet for numerical operations, like generating random data, and code snippet for plotting. Setting a random seed ensures that our synthetic data will be the same every time you run the code, which is helpful for consistent examples. Download the code on OnePageCode Substack. Here, we create our time index using code snippet for 30 consecutive days starting from January 1st, 2023. For the temperature data, we simulate a realistic scenario by starting with a base temperature, adding a slight linear increase over the 30 days, representing a subtle trend, and then incorporating random noise using code snippet to mimic real-world variability. Download the code on OnePageCode Substack. We then combine our generated code snippet and code snippet into a code snippet. A code snippet is an excellent data structure for time series data because it automatically handles the time index, making subsequent operations like plotting or resampling much easier. Printing the head of the series shows how the date acts as the index for each temperature reading. Download the code on OnePageCode Substack. Finally, we visualize our synthetic time series. Plotting a time series is crucial for initial exploration, allowing us to observe patterns like trends, seasonality, and irregular fluctuations. The x-axis represents time, and the y-axis represents the observed value. This simple line plot clearly illustrates the temporal progression of the data. The purpose of time series forecasting. The primary purpose of time series forecasting is to make informed decisions about the future. By predicting how a variable will behave over time, businesses, governments, and researchers can optimize resource allocation, forecast demand for products to manage inventory, schedule staffing, or plan production, mitigate risks, predict financial market volatility or potential equipment failures to take proactive measures, inform policy and strategy, forecast economic indicators, GDP, inflation, for policymaking, or predict disease spread for public health interventions. Understand underlying dynamics. Analyzing past patterns can reveal insights into the processes generating the data. Practical applications span various domains: business and finance, sales forecasting, stock price prediction, energy consumption forecasting, call center staffing, meteorology, weather forecasting, climate modeling, econometrics, predicting GDP, unemployment rates, inflation, industrial processes, predictive maintenance for machinery, quality control, marketing, forecasting ad campaign effectiveness, website traffic, healthcare, predicting patient admissions, disease outbreaks. Time series forecasting versus other regression tasks. Key distinctions. While forecasting involves predicting a numerical value, much like a standard regression problem, e.g., predicting house prices based on features like size, location, number of bedrooms, there are fundamental differences that necessitate specialized techniques for time series data. Ignoring these distinctions can lead to flawed models and inaccurate predictions. 1. Temporal dependence autocorrelation. Standard regression assumes that observations are independent of each other. The prediction for one house price doesn't directly depend on another house's price in the training set, beyond shared features. Time series forecasting. The most critical distinction is temporal dependence. The value at time code snippet is highly dependent on values at code snippet, and so on. This inherent correlation between successive observations is called autocorrelation. For example, today's temperature is very likely related to yesterday's temperature. 2. Order matters. Standard regression. The order of rows in your dataset typically doesn't matter. If you shuffle the rows of a house price dataset, the model will still learn the same relationships. Time series forecasting. The chronological order of data points is paramount. Shuffling a time series destroys its inherent temporal structure and makes it impossible to forecast. Models must respect this sequence. 3. Future prediction only. Standard regression, often used to estimate relationships between variables or predict existing outcomes, e.g., predicting the price of a house currently on the market. All features used for prediction are known at the time of prediction. Time series forecasting. The goal is to predict future values of the variable itself. This means that any features used for prediction, exogenous variables, must also be known for the future or themselves be forecasted. 4. Stationarity. Standard regression assumes that the underlying data generating process is stable. Time series forecasting. Many time series exhibit non-stationary behavior, meaning their statistical properties, like mean, variance, or autocorrelation, change over time. For example, a company's sales might have an increasing trend over years. Many traditional time series models require the series to be stationary, or transformed to be so, for valid inference and accurate forecasting. Components of a time series. To better understand the patterns within a time series, it's often helpful to decompose it into several underlying components. While we'll delve into decomposition methods later, a high-level understanding is crucial from the outset. 1. Trend. This represents the long-term increase or decrease in the data over time. It's the overall direction of the series, ignoring short-term fluctuations. For example, the growing global population exhibits an upward trend. In our synthetic temperature example, we added a slight upward trend. 2. Seasonality. These are regular, repeating patterns or cycles in the data that occur at fixed and known intervals. For instance, retail sales often peak during holidays, or electricity consumption might peak during certain hours of the day or seasons of the year. The length of a cycle is called the seasonal period, e.g., 7 days for weekly seasonality, 12 months for annual seasonality. 3. Residuals/noise are also known as the remainder or irregular component. This is what's left after, accounting for the trend and seasonal components. It represents the random, unpredictable fluctuations in the data that cannot be explained by trend or seasonality. This is often the part we aim to minimize in our models. These components can be combined additively, e.g., code snippet, or multiplicatively, e.g., code snippet, depending on whether the magnitude of the seasonal fluctuations changes with the level of the series. Python's prominence in time series analysis. Python has emerged as the dominant programming language for data science, machine learning, and, consequently, time series analysis and forecasting. Its popularity stems from several key advantages. Versatility. Python is a general-purpose language, meaning it's not limited to statistical computing. You can use it for data cleaning, web development, deploying models, and building entire applications, providing an end-to-end solution. Rich ecosystem of libraries. Python boasts an incredibly extensive collection of open-source libraries specifically designed for data manipulation, statistical analysis, machine learning, and deep learning. Code snippet. Indispensable for data manipulation, especially with time index data. Code snippet provides powerful numerical computing capabilities. Code snippet and code snippet for data visualization. Code snippet, a collection of scientific computing tools. Code snippet offers a wide array of statistical models, including classical time series models like ARI, MA, ETS, and state space models. Code snippet a comprehensive machine learning library with tools for regression, classification, clustering, and more, which can be adapted for time series feature engineering. Specialized libraries. Libraries like Code Snippet, developed by Facebook, and Code Snippet, AutoArima, streamline common forecasting tasks. Deep learning frameworks. Code Snippet and Code Snippet enable the development of advanced neural network models, including recurrent neural networks, RNNs, and transformers, which are highly effective for complex time series patterns. Community support. A large and active community means abundant resources, tutorials, and quick resolution of issues. Readability. Python syntax is often described as clear and intuitive, making it easier to learn and write maintainable code. While languages like R have historically been strong in statistical computing, Python's broader applicability and its robust machine learning and deep learning ecosystem make it the preferred choice for modern time series forecasting, especially when integrating with larger data pipelines or deploying models into production. This book will leverage Python extensively, providing practical, hands-on examples that build your proficiency in this powerful environment. Pedagogical progression of this book. This book is structured to guide you through the exciting world of time series forecasting in a logical and progressive manner. We will begin with found-at, INL concepts, and simpler statistical models, gradually building complexity as we introduce more advanced techniques. You will start by understanding the basic characteristics of time series data and classic statistical methods, like exponential smoothing and ARIMA models, which form the bedrock of many forecasting solutions. As your understanding deepens, we will transition to machine learning approaches, where you'll learn to engineer features from time series data and apply powerful algorithms. Finally, we will explore the cutting edge of time series forecasting with deep learning models, leveraging the capabilities of neural networks to capture intricate temporal dependencies and long-term patterns. This structured approach ensures that you build a strong conceptual and practical foundation, enabling you to tackle a wide range of real-world forecasting challenges. What is a time series? At its core, a time series is a sequence of data points indexed or listed in time order. This means that each data point in the series corresponds to a specific point in time, and the order of these points is crucial. Unlike other forms of data analysis where observations might be independent or arbitrarily ordered, in time series analysis, the temporal sequence is the primary independent variable and carries significant information. Consider the daily closing price of a stock, the quarterly earnings of a company, or the hourly temperature readings from a sensor. In each case, the value observed at one point in time is often influenced by and provides context for values observed at previous points in time. This inherent temporal dependency is what fundamentally distinguishes time series data from other types of datasets, such as cross-sectional data, e.g., a survey of customer preferences at a single point in time, or panel data, which combines cross-sectional observations over time, but often treats time as a separate dimension rather than the primary index. Defining characteristics of time series data. While the definition is straightforward, understanding the nuances of time series data is key to effective analysis and forecasting. 1. Time-ordered sequence. The most critical characteristic is that the data points are ordered by time. This is not merely a convenience. It is a fundamental property. Changing the order of observations in a time series would fundamentally alter its meaning and the patterns it exhibits. For instance, scrambling the order of daily stock prices would render the data meaningless for financial analysis, as the progression of prices over time is what reveals trends, volatility, and market cycles. 2. Often equally spaced intervals. Many time series, especially those amenable to traditional forecasting models, consist of observations taken at regular, equally spaced intervals. Examples include hourly, temperature readings, website traffic; daily, stock prices, sales figures; weekly, retail sales, energy consumption; monthly, unemployment rates, inflation data; quarterly, company earnings, GDP figures; annually, population growth, agricultural yields. The assumption of equally spaced data simplifies the application of many time series models, as it implies a consistent underlying sampling frequency. However, it's important to acknowledge that not all real-world time series are equally spaced. Data from event logs, irregular sensor readings, where data is only transmitted upon significant change, or financial trade data, where transactions occur at irregular intervals, are examples of unequally spaced or irregular time series. While this book will primarily focus on equally spaced time series due to their prevalence in many business and economic applications and the simpler modeling approaches, be aware that specialized techniques exist for handling irregular data, often involving sampling, interpolation, or event-based modeling. 3. Temporal dependencies and autocorrelation. A defining feature of time series is that observations are typically not independent of each other. The value at the current time point often depends on values from previous time points. This phenomenon is known as autocorrelation, the correlation of a variable with itself over different time lags. For example, today's stock price is highly correlated with yesterday's price, and last month's sales figures are likely to influence this month's sales. This temporal dependency is precisely why traditional regression models, which often assume independent observations, are insufficient for time series forecasting. Time series models are specifically designed to capture and leverage these internal dependencies to make accurate predictions. Representing time series programmatically, the time index. When working with time series data in Python, especially with the powerful code snippet library, the concept of the time index becomes paramount. Code snippet data frames and series are ideal for handling time series because they allow for a dedicated code snippet. This index is not just a label. It's a specialized data type that enables powerful time-based operations like resampling, slicing by date ranges, and frequency analysis. Let's look at a simple example of how a time series might be structured in code snippet. Download the code on OnePageCode Substack. This first code, chunk demo, illustrates how to create a basic time series using code snippet. We define a list of dates, convert them into code snippet objects suitable for a code snippet index using code snippet, and then pair them with a corresponding list of values. The code snippet constructor, when given both data and in code snippet, automatically creates a time series where the dates serve as the explicit time-ordered labels for each data point. Download the code on OnePageCode Substack. This small addition verifies that code snippet correctly recognized our dates and assigned a code snippet. This specialized index type is what unlocks code snippet's powerful time series capabilities, allowing for efficient operations like selecting data by date ranges or resampling data to different frequencies, e.g., converting daily data to weekly averages. Real-world examples of time series. Time series data is ubiquitous across virtually every domain. Recognizing these patterns in various contexts is the first step toward applying time series forecasting techniques. Financial markets. Stock prices, daily, hourly, or even minute-by-minute closing prices, opening prices, high/low values for individual stocks or market indices, e.g., S&P 500. Exchange rates, fluctuations of currency pairs, e.g., US dollar to euro, over time. Company earnings, quarterly or annual earnings per share, revenue, or profit figures. Interest rates, daily or monthly changes in benchmark interest rates. Economic indicators, gross domes, TIC product, GDP quarterly or annual economic output of a country. Inflation rates, monthly or annual percentage change in consumer prices. Unemployment rates, monthly percentage of the labor force that is unemployed. Consumer Price Index, CPI, monthly measure of the average change over time in the prices paid by urban consumers for a market basket of consumer goods and services. Environmental and climate data. Temperature readings, hourly, daily, or monthly average temperatures in a specific location. Rainfall/precipitation, daily or monthly accumulated rainfall. Air quality, hourly measurements of pollutants like PM 2.5 or ozone. Ocean levels, annual measurements of sea level rise. Business and retail, sales data, daily, weekly, or monthly sales volumes for products or services. Website traffic, hourly or daily unique visitors, page views, or conversion rates. Customer service calls, number of calls received per hour or day. Inventory levels, daily or weekly counts of goods in stock. Healthcare and medical. EKG/ECG readings, continuous measurements of electrical activity of the heart. Blood pressure monitoring, hourly or daily readings for patients. Disease incidents, weekly or monthly counts of new disease cases, e.g., flu outbreaks. Internet of Things, IoT, and sensor data. Smart home devices, energy consumption, temperature, or humidity readings from connected devices. Industrial sensors, pressure, temperature, vibration data from machinery. 4. Predictive maintenance. Vehicle telemetry, speed, location, engine performance data over time. This diverse range of examples underscores the universality of time series data and the broad applicability of forecasting techniques across various industries and scientific disciplines. Introducing the Johnson & Johnson Earnings Dataset. Throughout this book, we will frequently refer to and analyze the Johnson & Johnson J&J quarterly earnings per share EPS dataset. This dataset is a classic example in time series analysis due to its clear and illustrative patterns. It tracks the quarterly earnings per share for the pharmaceutical and consumer goods giant Johnson & Johnson from 1960 to 1980. Let's load this dataset, or a similar representative one for illustration, and visualize it to understand its key properties. For this introductory section, we will use a simplified approach to loading data, assuming it's available in a common format like a CSV file. Download the code on one Pagecode Substack. This code snippet prepares the J&J dataset for analysis. It attempts to load a CSV file, which is a common way to obtain real-world data. Crucially, code snippet and code snippet tell code snippet to use the quarter column as the code snippet, ensuring the data is correctly recognized as a time series. A fallback synthetic dataset is included for robustness, allowing the code to run even if the specific CSV isn't present, mimicking the real data's characteristics. Displaying co. The snippet allows us to quickly inspect the structure and ensure the time index is correctly set. Now, let's visualize the data. Download the code on one Pagecode Substack. This plotting code uses code snippet to generate a line plot, which is the standard way to visualize a time series. The code snippet, our code snippet, is used for the x-axis and the earnings column for the y-axis. Markers and line styles are added for clarity, and standard plotting enhancements like titles, labels, and a grid are applied to make the visualization informative. Visual properties of the J&J dataset. Upon examining the plot of the Johnson & Johnson earnings, several key characteristics become immediately apparent. 1. Trend. There's a clear upward trend over the entire period. Earnings per share generally increase from 1960 to 1980, indicating consistent growth for the company. This suggests that future earnings are likely to be higher than past earnings, a critical piece of information for forecasting. 2. Cyclical/seasonal behavior. Within each year, there's a distinct pattern. Earnings tend to be lower in the first quarter, Q1, and then peak in the fourth quarter, Q4. This repeating pattern within a fixed period, a year, in this case, is known as seasonality. For a business, this often reflects seasonal demand for products, holiday sales, or fiscal reporting cycles. 3. Increasing variability. As time progresses and the overall earnings increase, the magnitude of the seasonal fluctua. Tie-ins also appears to increase. The peaks and troughs become more pronounced in later years. This suggests that the variance or standard deviation of the series is not constant over time, a property known as heteroscedasticity. This is an important consideration for more advanced forecasting models. These visual properties, trend, seasonality, and changing variability, are common in many real-world time series and will be central to the forecasting techniques explored in later sections. Why is time series forecasting different? You might wonder why we need specialized techniques for time series forecasting when standard regression methods can predict a dependent variable based on independent variables. The crucial distinction lies in the temporal dependence we discussed earlier. In typical regression problems, observations are often assumed to be independent and identically distributed, i.d. This means that the value of one observation does not influence another, and all observations come from the same underlying distribution. However, for time series data, this assumption is fundamentally violated. The past values of a time series directly influence its future values. This inherent autocorrelation means that simply using time as an independent variable in a standard linear regression model often fails to capture the complex temporal dynamics. Such models might provide a general trend, but would likely miss crucial patterns like seasonality or the impact of recent fluctuations. Time series forecasting models are specifically designed to explicitly account for these dependencies, leveraging the rich information contained within the sequence of observations to make more accurate and robust predictions. Components of time series. Time series data, by its very nature, is a collection of observations recorded over time. While a simple line plot can show the overall movement, a deeper understanding often requires us to break down the series into its fundamental building blocks. This process, known as time series decomposition, helps us identify and isolate the distinct patterns that contribute to the observed data. Understanding these components is crucial for diagnosing the behavior of a series, making informed forecasting decisions, and developing robust models. The observed time series. Before diving into components, let's establish what we mean by the observed time series. This is simply the raw, actual data points collected over time, often denoted as $YT$, where $T$ represents a specific point in time. For instance, the monthly sales figures for a retail store, the daily temperature readings in a city, or the hourly electricity consumption of a building are all observed time series. Trend. The trend component captures the long-term, underlying direction or movement of a time series. It represents the persistent increase, decrease, or stagnation in the data over a significant period. Characteristics. Long-term. Trends are not short-term fluctuations but reflect patterns spanning multiple years, decades, or even longer. Directional. They indicate whether the series is generally moving upwards, e.g., growing economy, increasing population, downwards, e.g., declining. In product sales, decreasing birth rates, or remaining relatively constant. Not necessarily linear. While a linear trend, straight line, is common, trends can also be nonlinear, e.g., exponential growth, S-shaped curves, parabolic movements. Influenced by macro factors, trends are often driven by broad societal, economic, technological, or demographic changes. For example, the increasing adoption of e-commerce might show an upward trend in online sales, while a shift in consumer preferences could show a downward trend for a specific product category. Real-world applications. Identifying trends is vital for strategic planning. A business needs to know if its market is growing or shrinking. A government needs to understand population growth trends to plan infrastructure. Common pitfalls. Confusing a short-term fluctuation with a long-term trend. A temporary dip in sales due to an unusual event is not a trend, but a sustained decline over several years likely is. Seasonality. The seasonal component refers to patterns that repeat over a fixed, known period. These patterns are regular, predictable, and occur within a specific time frame, such as a day, week, month, quarter, or year. Characteristics. Fixed period. The pattern repeats at regular intervals. For example, hourly electricity consumption might peak in the afternoon every day, or retail sales might surge every December. Recurring. The pattern is consistent across different cycles. The peak in sales happens every December, not just some Decembers. Predictable. Because the period is fixed, the seasonal pattern can be anticipated. Driven by calendar/climate. Seasonality is often influenced by calendar events, holidays, academic terms, weather patterns, temperature, rainfall, or business cycles, weekly payroll, monthly billing. Real-world applications. Understanding seasonality is critical for inventory management, stocking up before peak season, staffing decisions, hiring extra help for holiday rushes, and resource allocation, predicting energy demand. Distinction. Seasonality versus cyclicity. Seasonality. Fixed, known period, e.g., 12 months, 7 days. Cyclicity. Fluctuations that are not of a fixed period, often longer than a year, and can vary in length and amplitude. Business cycles, recessions, expansions are prime examples. A common pitfall is to confuse a business cycle, e.g., a 5 to 7 year economic boom-bust cycle, with true seasonality. While both are recurring, only seasonality has a predictable, fixed duration. Residuals, noise, or irregular component. The residual component, also known as the noise or irregular component, represents the random, unpredictable fluctuations in the time series that cannot be explained by the trend or seasonal patterns. Characteristics. Random. Ideally, residuals should exhibit no discernible pattern, meaning they are random and independent of each other. Unexplained. They capture the variability in the data that is left over AF. Accounting for trend and seasonality. Often white noise. In a well-decomposed series, the residuals should resemble white noise, a sequence of random variables with zero mean, constant variance, and no autocorrelation, no correlation with past values. Contains anomalies, unusual events, outliers, or unforeseen circumstances, e.g., a sudden product recall, a natural disaster, a unique marketing campaign, will often show up as large spikes or deviations in the residual component. Real-world applications. Model assessment. If a forecasting model adequately captures trend and seasonality, the residuals of the model's errors should resemble white noise. Any remaining patterns in the residuals indicate that the model is incomplete or has missed important information. Anomaly detection. Large deviations in residuals can signal unusual events or anomalies that warrant further investigation. Time series decomposition. Breaking down the series. Time series decomposition is the statistical task of breaking down a time series into these underlying components. This process simplifies the analysis and forecasting of complex time series by allowing us to study each component independently. The concept of decomposition. The goal of decomposition is to separate the observed series $YT$ into its constituent parts: trend, $TT$, seasonal, $ST$, and residual, $RT$. This allows us to understand the individual contributions of each pattern to the overall series behavior. For example, if you're analyzing monthly retail sales, decomposition can tell you, is the overall sales volume increasing or decreasing over the years? Trend? Are there predictable spikes in sales every December and dips every January? Seasonality? Or are the unpredictable variations left after accounting for these patterns? Residuals. Additive versus multiplicative models. The way these components are combined to form the observed series defines the type of decomposition model used. The choice between an additive and a multiplicative model is crucial and depends on how the amplitude of the seasonal fluctuations changes over time. 1. Additive model. Formula. $YT equals TT plus ST plus RT $. Characteristics. In an additive model, the magnitude of the seasonal fluctuations and residuals remains roughly constant over time, regardless of the level of the trend. The seasonal component adds a fixed amount to the trend. When to use. This model is appropriate when the variation around the trend does not increase or decrease with the level of the series. For example, if monthly sales vary by approximately plus or minus $1,000 around the trend, whether the trend is $10, $000 or $100, $000. This often applies to phenomena where the factors causing seasonality are independent of the magnitude of the series itself, e.g., fixed holiday effects. 2. Multiplicative model. Formula. $YT equals TT backslash times ST backslash times RT $. Characteristics. In a multiplicative model, the magnitude of the seasonal fluctuations and residue, ALS, increases or decreases proportionally with the level of the trend. The seasonal component multiplies the trend. When to use. This model is suitable when the amplitude of the seasonal pattern grows or shrinks as the overall level of the series changes. For example, if monthly sales vary by plus or minus 10% of the trend, meaning the actual dollar variation is much larger when sales are $100,000 than when they are $10,000. This is common in economic series like GDP, sales, or population growth, where growth tends to be exponential. Choosing the right model. Visually inspect the time series plot. If the seasonal fluctuations appear to grow wider or narrower as the series progresses, heteroscedasticity, a multiplicative model is likely more appropriate. If the fluctuations remain relatively constant in width, an additive model is better. If in doubt, try both and compare the clarity of the decomposed components and the characteristics of the residuals. A common trick for multiplicative series is to apply a logarithmic transformation, which can transform a multiplicative relationship into an additive one, allowing the use of additive decomposition methods on the transformed data. Common decomposition algorithms. While the underlying concept is simple, various algorithms are used to perform decomposition. Moving averages, a simple and intuitive method where the trend is estimated by smoothing the series using a moving average. Seasonality is then derived by averaging the trend. Add values for each period. STL, seasonal trend decomposition, using LUS, a more robust and versatile method that uses local regression, LUS, to estimate the trend and seasonal components. It can handle various types of seasonality and is less sensitive to outliers than traditional moving average methods. X, 11/X, 13 ARIMA seats, sophisticated and widely used methods developed by the U.S. Census Bureau. These are complex seasonal adjustment programs often used for official economic statistics. Practical decomposition with Python. Python's code snippet library provides powerful tools for time series analysis, including decomposition. We will use code snippet to illustrate the process. Setting up the environment. First, we need to import the necessary libraries. Download the code on OnePageCode Substack. Here, we import code snippet for data manipulation, code snippet for numerical operations, code snippet for plotting, and code snippet from code snippet for the decomposition itself. We also import tools for analyzing residuals later. Generating a synthetic time series. To clearly understand how decomposition works, let's create a synthetic time series with known trend, seasonality, and noise components. This allows us to see if the decomposition algorithm can successfully recover these original patterns. Download the code on OnePageCode Substack. We define a code snippet using code snippet for 10 years of monthly data, starting from January 2010. Code snippet specifies month start frequency. Code snippet ensures our random components are consistent for repeated runs. Download the code on OnePageCode Substack. Here, we create a simple linear trend that increases from 0 to 100 over the 120 periods. Download the code on OnePageCode Substack. This code generates a sinusoidal seasonal pattern. Code snippet creates a wave, and code snippet ensures it completes 3 cycles over 10 years, 3 full cycles per year, 10 years total. Multiplying by code snippet sets the amplitude of the seasonality. Download the code on OnePageCode Substack. We generate random noise using a normal distribution with a mean of 0 and a standard deviation of 2. This represents the unpredictable part of the series. Now, let's combine these components to create our observed time series. First, using an additive model. Download the code on OnePageCode Substack. The code snippet is created by simply summing the trend, seasonal, and noise components. We wrap it in a code snippet with our code snippet. Download the code on OnePageCode Substack. For multiplicative series, the components should typically be factors that multiply. Here, code snippet and code snippet are constructed to oscillate around 1, so they act as scaling factors. The trend also starts from a positive value. Finally, let's visualize our synthetic additive series. Download the code on OnePageCode Substack. This plot displays the combined synthetic series, clearly showing an upward trend with consistent SE. Atonal fluctuations, as expected from an additive model. Performing decomposition. We use code snippet to perform the decomposition. This function takes the time series, the model type, code snippet or code snippet, and the code snippet of the seasonality as arguments. Download the code on one patch code Substack. We apply code snippet to our code snippet. We explicitly set code snippet and code snippet because our synthetic data has a clear yearly, 12-month seasonality. Download the code on one patch code Substack. The code snippet method of the decomposition result object conveniently generates subplots for the observed series, trend, seasonal, and residual components. Observe how well the code snippet function has identified the linear trend and the sinusoidal seasonal pattern that we built into the synthetic data. The residuals should appear as random noise around 0. Now, let's try decomposing the multiplicative series we created. Download the code on one patch code Substack. Here, we use code snippet as our synthetic series was generated with a multiplicative relationship. Download the code on one patch code Substack. Again, observe how the decomposition successfully extracts the trend, seasonal, and residual components. Notice how the seasonal component's amplitude appears to grow with the trend in the original series, which is characteristic of a multiplicative relationship. Real-world example. Air passengers dataset. Let's apply decomposition to a classic real-world. Dataset. Monthly international airline passenger numbers from 1949 to 1960. This dataset is famous for exhibiting a clear, multiplicative seasonality. Decomposition, or a subsequent forecasting model, is a good fit for the data. The residuals should contain no discernible patterns. Any remaining pattern suggests that the decomposition, or model, has not fully captured all the underlying structure. Anomaly detection. Outliers or unusual events in the original series will often manifest as large spikes in the residual component, making them easier to spot. Checking for white noise. We can visually inspect and statistically test the residuals for white noise characteristics. Download the code on one patch code Substack. Visually, the residuals from the air passengers decomposition appear somewhat random, but there might be some small variations in variance. Download the code on one patch code Substack. The autocorrelation function, ACF, plot shows the correlation of a time series with its own past values, lags. For white noise, all autocorrelations, except at lag 0, which is always 1, should be close to 0 and fall within the confidence bands, the blue shaded area. If significant spikes are outside these bands, it suggests remaining correlation, meaning the residuals are not pure white noise and there's uncaptured information. In the air passengers example, the ACF generally falls within the bands, suggesting the residuals are largely random. Download the code on one patch code Substack. The Legendre test is a formal statistical test for autocorrelation in the residuals. The null hypothesis, $H0, is that the data are in deep, densely distributed, i.e., residuals are white noise. If the p-value is greater than a chosen significance level, commonly 0.05, we fail to reject the null hypothesis, suggesting the residuals are indeed white noise. We test at multiple lags, e.g., 10 and 20, to check for short and longer-term dependencies. For the air passengers residuals, if the p-values are high, it supports the notion that the decomposition has effectively isolated the trend and seasonality. Practical implications of residuals. Model validation. Thorough analysis of residuals is a critical step in validating any time series model. If residuals show patterns, it indicates that your model is inadequate and needs refinement. Feature engineering. If residuals are not white noise, the patterns within them might suggest new features to incorporate into a more complex forecasting model, e.g., adding a new predictor variable, or using a more sophisticated model that can capture higher-order dependencies. Anomaly detection. Monitoring residuals over time is an effective way to detect sudden, unexpected changes in the underlying process, which could signal system failures, unusual market events, or data errors. Impact on forecasting model selection. Understanding the components of a time series directly informs the choice and complexity of forecasting models. Trend. If a strong trend is present, models that can explicitly capture and extrapolate trends, e.g., ARIMA models with differencing, exponential SM, smoothing methods like Holtz or Holt-Winters, or regression models with time as a predictor, are appropriate. Seasonality. For series with clear seasonality, models that explicitly account for seasonal patterns are necessary. This includes seasonal ARIMA, SARIMA, seasonal exponential smoothing, Holt-Winters, or models like Profit that explicitly model seasonal effects. Stationarity. Decomposing a series can help achieve stationarity, constant mean, variance, and autocorrelation over time, which is a key assumption for many traditional forecasting models like ARIMA. By removing trend and seasonality, the remaining residuals are often closer to a stationary process. Feature engineering. The seasonal component can be extracted and used to create new features for machine learning models, e.g., creating dummy variables for months or days of the week, or sine/cosine transformations to capture cyclical patterns. The trend component can also be used as a feature or modeled separately. By systematically breaking down a time series into its fundamental components, we gain profound insights into its behavior, which is an indispensable step towards accurate analysis and reliable forecasting. Bird's-eye view of time series forecasting. The Comprehensive Time Series Forecasting Project Roadmap. Developing accurate and actionable time series forecasts involves far more than simply running a statistical model. It's a comprehensive, cyclical process that bridges business objectives with technical execution, requiring collaboration across various roles. A structured approach, often referred to as a forecasting project roadmap or life cycle, is essential for success. This roadmap ensures that forecasting efforts are aligned with strategic goals, data quality is maintained, models are robust, and their outputs are effectively utilized and continuously improved. Neglecting any stage can lead to models that are technically sound but fail to deliver real-world value or quickly become obsolete. Let's explore the key stages of a typical time series forecasting project. 1. Define the business problem and goals. This initial stage is arguably the most critical yet often overlooked. Before collecting any data or thinking about models, it's paramount to clearly articulate why a forecast is needed and what specific business decision it will inform. Why it's crucial. Clarity and direction. A well-defined problem provides a clear objective for the entire project, preventing aimless data exploration or model building. Alignment with business value. It ensures the forecasting effort directly contributes to an organizational goal, such as cost reduction, revenue increase, or improved efficiency. Define success metrics. Understanding the business problem helps identify the key performance indicators, KPIs, that will measure the forecast success. For instance, is accuracy paramount, or is it more important to avoid stockouts? Scope definition helps to bound the problem, preventing scope creep, where the project expands beyond its original intent. Key activities. Stakeholder interviews. Engage with business users, domain experts, and decision-makers to understand their needs, current challenges, and desired outcomes. Problem framing. Translate vague business questions into specific, measurable forecasting problems, e.g., predict next month's sales for product X, forecast hourly energy demand for the next 24 hours. KPI identification. Define the metrics that will quantify the impact and success of the forecast, e.g., code snippet, code snippet, code snippet, code snippet. Time horizon and granularity. Determine the required forecasting horizon, e.g., next day, next month, next year, and the granularity, e.g., hourly, daily, weekly, monthly. Common pitfalls. Vague objectives, starting with "we need a forecast," without specifying for what purpose or how it will be used. Lack of business context. Developing a technically accurate model that doesn't solve the actual business problem or isn't actionable. Ignoring stakeholders. Building a solution in isolation without input from those who will use it. Typical roles involved. Business analyst, product manager, domain expert, lead data scientist. Example, camping trip scenario. Imagine you're planning a multi-day camping trip and want to choose the right sleeping bag. Business problem. Select a sleeping bag that will keep me comfortable, but not overheated given the expected overnight temperatures. Goal. Forecast the minimum overnight temperature for each night of the trip to inform sleeping bag selection. Success metric. My comfort level, subjective, but we can aim for the sleeping bag's comfort rating to match the forecast temperature. Time horizon / granularity. Daily minimum temperature for the next 3 to 5 days. Example, retail sales forecasting. A retail chain wants to optimize inventory and staffing. Business problem. Accurately predict future sales to minimize stockouts, reduce excess inventory holding costs, and optimize staffing levels in stores. Goal. Forecast daily sales for each product SKU at each store location for the next 4 to 6 weeks. Success metrics. Code snippet. Mean absolute percentage error. For sales, code snippet. Time horizon / granularity. Daily sales forecast for individual SKUs at specific store locations, looking 4 to 6 weeks ahead. 2. Gather and prepare data. Once the problem is clear, the next crucial step is to acquire and ready the data that will fuel your forecasting model. Data quality directly impacts model performance. Garbage in, garbage out is particularly true in time series forecasting. Why IT is crucial. Data as fuel. High-quality, relevant historical data is the fundamental input for any time series model. Reliability. Clean and well-prepared data ensures that the patterns identified by the model are genuine and not artifacts of data errors or inconsistencies. Feature engineering foundation. This stage lays the groundwork for creating meaningful features that capture underlying drivers of the time series. Key activities. Data source identification. Locate all relevant data sources, e.g., internal databases, APIs, external datasets. This might include the target time series itself, e.g., sales, temperature, and potential exogenous variables, e.g., promotions, holidays, economic indicators. Data extraction, ETL/ELT retrieve data from various sources. This can involve writing scripts to connect to databases, consume APIs, or parse files. Data cleaning, address common data issues. Missing values, impute, e.g., interpolation, mean/median, or remove missing data points. Outliers, identify and handle extreme values that might distort patterns, e.g., capping, removal, or specialized robust methods. Inconsistent formats, standardized data types, date formats, and categorical encodings. Duplicates, remove redundant entries. Data transformation, reshape data for analysis. Aggregate to the desired granularity, e.g., from hourly to daily, or normalize/standardize numerical features. Preliminary feature engineering, conceptual at this stage, you might RT thinking about and creating basic features like code snippet, past observations, code snippet, or code snippet, day of week, month, year. Common pitfalls, data silos, relevant data being scattered across different departments or systems, making it hard to access. Poor data quality, assuming data is clean, leading to models built on flawed information. Insufficient historical data. Time series models often require a significant amount of historical data to identify trends and seasonality reliably. Data leakage, accidentally including future information in the training data, leading to overly optimistic evaluation results. Typical roles involved: data engineer, data scientist. Example, camping trip scenario. Data collection, access historical weather data for the camping location, temperature, precipitation, wind speed, potentially from weather APIs or historical records. Also, gather personal notes from past trips, e.g., felt cold with 40F sleeping bag at 35F. Data preparation, clean weather data, handle missing temperature readings, align dates, and perhaps average temperatures over the night. Example, retail sales forecasting. Data collection, Extract historical sales transaction data, SKU, quantity, price, date, store ID, promotional calendars, holiday schedules, and possibly external economic indicators, e.g., consumer confidence index, local unemployment rates. Data preparation. Aggregate transactional data to daily SKU store sales. Identify and handle missing sales records. Clean up inconsistent product IDs. Create features like code snippet, code snippet, code snippet. 3. Develop a forecasting model. This is where the core predictive engine is built. It involves selecting, training, and optimizing a model based on the prepared historical data. Why it's crucial. This stage translates the patterns and relationships identified in the data into a predictive algorithm that can generate future forecasts. Key activities, high-level conceptual, data splitting. Divide the historical data into code snippet, or code snippet, and code snippet sets. 4 time series. This is typically done chronologically. Code snippet for training, code snippet for validation/test, to simulate real-world forecasting. Feature engineering, advanced beyond basic time-based features. This might involve creating more complex interactions, polynomial features, or transformations specific to the chosen model. Model selection. Choose appropriate forecasting algorithms. This could range from traditional statistical models, e.g., code snippet, to machine learning models, e.g., code snippet, or deep learning models, e.g., code snippet, depending on data complexity, volume, and required interpretability. Model training. Fit the selected models to the training data. This process learns the underlying patterns and relationships between features and the target V. Variable. Hyperparameter tuning. Optimize the model's internal parameters, hyperparameters, using the validation set to achieve the best performance without overfitting. This might involve techniques like code snippet, or code snippet. Common pitfalls. Overfitting/underfitting. Building a model that performs perfectly on training data but poorly on new data, overfitting, or a model that is too simplistic and doesn't capture underlying patterns, underfitting. Ignoring baseline models. Not comparing complex models against simple baselines, e.g., code snippet, to ensure added complexity is justified. Lack of interpretability. Choosing a black box model when explainability is crucial for business trust and decision-making. Typical roles involved: data scientist, machine learning engineer. Example: camping trip scenario. Model selection: a simple rule-based model. If the forecast minimum temperature is below 30 F, use a 0 F bag. If between 30-45 F, use a 30 F bag. Otherwise, use a light bag. Or a basic linear regression using historical temperature data. Training. If using regression, train the model on past temperature versus comfort data. Example: retail sales forecasting. Model selection. Experiment with various models like code snippet for strong seasonality and holidays, code snippet for autocorrelation, or code snippet for incorporating many exogenous variables like promotions. For large-scale forecasting across many SKUs, a hierarchical approach or a deep learning model might be considered. Training. Train the chosen models on historical sales data, incorporating features like code snippet, and code snippet. 4. Evaluate and validate the model. After developing a model, it's critical to rigorously evaluate its performance using unseen data to ensure its reliability and generalization capabilities. This step is about confirming that the model will perform well in the real world. Why it's crucial. Trust and reliability. Provides confidence that the model's predictions are accurate and trustworthy. Preventing over-optimism. Evaluation on a separate test set prevents overestimating performance due to overfitting on training data. Informing deployment. A well-validated model is a prerequisite for successful deployment. Error analysis. Helps understand where and why the model makes mistakes, guiding further improvements. Key activities. Defining evaluation metrics. Choose appropriate metrics based on the business problem, e.g., code snippet, code snippet. Some metrics are better for specific error types or business contexts. Backtesting / out-of-sample validation. Evaluate the model's performance on the code snippet, data the model has never seen, mimicking how it would perform on future data. 4-time series. This often involves rolling forecast origin or walk-forward validation, where the model is retrained and evaluated on successive time windows. Sensitivity analysis. Understand how robust the model is to changes in input data or assumptions. Error analysis. Investigate patterns in prediction errors. Are errors higher on weekends? During promotions? For certain product categories? This provides insights for model refinement. Business impact assessment. Translate statistical accuracy into business implications, e.g., a 5% code snippet means we might overstock by X units or understock by Y units, costing Z dollars. Common pitfalls. Using inappropriate metrics. Choosing metrics that don't align with a business goal, e.g., using code snippet when code snippet is more relevant for percentage errors. Evaluating on training data only, leading to an inflated sense of accuracy. Ignoring business context of errors. Not understanding the real-world cost or impact of different types of forecasting errors. Typical roles involved: data scientist, business analyst. Example: camping trip scenario. Evaluation. After the trip, compare the forecast minimum temperatures against the actual minimum temperatures recorded. Did the sleeping bag recommendation align with your comfort level? If not, why? E.g., wind chill wasn't factored in. Metrics. A simple count of comfortable versus uncomfortable nights. Example: retail sales forecasting. Evaluation. Compare the model's daily SKU store sales forecasts against actual sales data for the test period. Metrics. Calculate code SN, IPIT, and code snippet for different product categories, stores, and time periods. Analyze code snippet. Is the model consistently over or under forecasting? Present these metrics to stakeholders in an understandable way. 5. Deploy to production. Once a model has been thoroughly validated and deemed fit for purpose, it needs to be integrated into the operational environment so that its forecast can be used for real-world decision-making. Why it's crucial. Actionable insights. Deployment makes the forecast accessible to business users and systems, allowing them to act on the predictions. Automation. Automates the forecasting process, reducing manual effort and ensuring timely availability of predictions. Scalability. Enables the model to generate forecasts at the required scale and frequency. Key activities. Model serialization. Save the trained model in a deployable format, e.g., code snippet file, code snippet, code snippet. API development. Wrap the model in an API, e.g., code snippet using Flask or Fast API, so other applications can easily request forecasts. Integration with existing systems. Connect the forecasting service with business applications, e.g., inventory management systems, ERPs, dashboards. This might involve setting up data pipelines to feed inputs to the model and consume its outputs. Infrastructure provisioning. Set up the necessary computing resources, e.g., cloud instances, containers like Docker, orchestration with Kubernetes to host the model. Automated pipelines. Establish code snippet, continuous integration / continuous deployment. Pipelines for model updates and automated retraining. Common pitfalls. Lack of MLOps maturity. Underestimating the complexity of operationalizing machine learning models compared to traditional software. Integration complexities. Difficulty connecting the model with legacy systems. Scalability issues. The deployed model cannot handle the required volume of predictions or concurrent requests. Security concerns. Neglecting data security and access control for the deployed model. Typical roles involved. MLOps engineer, software engineer, data scientist. Example: camping trip scenario. Deployment. Create a simple script or web application that takes the trip dates and location as input, queries a weather API for forecast temperatures, and then applies your sleeping bag rule to recommend a bag. Share this tool with friends. Example: retail sales forecasting. Deployment. The forecasting model is packaged into a container, e.g., Docker image, and deployed on a cloud platform, e.g., AWS SageMaker, Azure ML, Google Cloud AI platform. An API endpoint is exposed that inventory management systems can call daily to get updated sales forecasts for all SKUs and stores. An automated data pipeline ensures the model receives fresh input data regularly. 6. Monitor and maintain. Deployment is not the end of the project. It's the beginning of its operational life. Models, especially, why those relying on time-dependent data, can degrade over time due to changes in underlying patterns. Continuous monitoring and maintenance are crucial. Why it's crucial? Sustained performance ensures the model continues to provide accurate and relevant forecasts over time. Detecting degradation identifies model drift or concept drift with a relationship between input features and the target variable changes. Addressing data quality issues catches problems in the data pipeline that could impact model inputs. Business relevance ensures the model adapts to evolving business conditions and goals. Key activities. Performance monitoring. Continuously track model performance metrics, e.g., code snippet, code snippet, code snippet, against actual outcomes. Set up dashboards and alerts for significant deviations. Data quality monitoring. Monitor the incoming data pipeline for anomalies, missing values, or changes in data distribution that could affect the model. Concept drift detection. Implement mechanisms to detect when the underlying patterns the model learned are no longer valid, e.g., due to market shifts, new products, policy changes. Retraining schedules. Establish a regular schedule for retraining the model with new historical data to keep it updated. A/B testing. Experiment with new model versions or features by deploying them alongside the existing model to evaluate real-world performance before full rollout. Model versioning. Maintain versions of models and their associated code/data for reproducibility and rollback capabilities. Common pitfalls. Stale models. Deploying a model and never revisiting it, leading to rapidly degrading performance. Ignoring data pipeline issues. Assuming data quality will remain constant. Lack of alert systems. Not being notified when model performance degrades or data issues arise. No feedback loop. Not collecting feedback from business users on the usefulness or accuracy of the forecasts. Typical roles involved: MLOps engineer, data scientist, operations team. Example: camping trip scenario. Monitoring. After each trip, review how well the sleeping bag recommendation performed. Did you consistently feel too cold or too hot? Maintenance. If you consistently feel cold, perhaps update your rule to be more conservative or incorporate additional factors like wind. Example: retail sales forecasting. Monitoring. Set up automated dashboards that track daily code snippet and code snippet for sales forecasts across different stores and product categories. Configure alerts to notify the data science team if code snippet exceeds a certain threshold or if significant code snippet is detected. Maintenance. Schedule monthly retraining of the model with the latest sales data. If a new major promotional strategy is introduced, the model might need a significant update or even redevelopment to incorporate these new dynamics. Setting a goal. Before embarking on any time series forecasting endeavor, the single most crucial step is to define a clear, actionable goal. This initial phase, often overlooked in the rush to gather data and apply algorithms, determines the ultimate success and relevance of your entire forecasting project. Without a well-articulated goal, your efforts risk becoming aimless, producing forecasts that, while technically sound, provide no real value or actionable insights. The foundation. Why a clear goal is paramount. Think of a forecasting project as a journey. Your goal is the destination. Without knowing where you're going, any path you take will be arbitrary, and you might end up somewhere completely unhelpful. In the context of time series forecasting, defining your goal means answering the fundamental question: what decision will this forecast help me make, or what problem will help me solve? This seemingly simple question is the bedrock upon which all subsequent steps are built. It dictates what specific variable needs to be forecast, the required accuracy and precision of the forecast, the time horizon of the forecast, e.g., next day, next month, next year, the resources, data, tools, personnel you'll need, how the forecast will be evaluated for success. Characteristics of a good forecasting goal. A robust forecasting goal isn't just a vague aspiration. It possesses specific characteristics that make it effective and actionable. While not strictly adhere, ing to the full code snippet, specific, measurable, achievable, relevant, time-bound, criteria often used in project management, we can adapt its essence to forecasting. Specific. The goal must clearly state what needs to be achieved. Instead of forecast sales, a specific goal might be forecast daily sales of product X for the next month. Actionable. The forecast derived from the goal must directly lead to a decision or an action. If the forecast doesn't inform a concrete step, its utility is limited. For example, forecast future temperature to decide which sleeping bag to pack is actionable. Measurable. You must be able to quantify whether the goal has been met. This often relates to the impact of the forecast. For instance, reduce inventory holding costs by 10% by optimizing stock levels based on demand forecasts. Relevant. The goal must align with broader organizational objectives or personal needs. Forecasting for the sake of forecasting is rarely beneficial. It should address a genuine problem or opportunity. Time-bound, implied by horizon. While the goal itself might not always have an explicit deadline, the forecast it requires will always have a defined time horizon, e.g., forecast for the next quarter, predict next week's demand. This implicitly makes the goal time-bound in terms of its utility. The perils of a vague goal. Failing to define a clear goal is one of the most common pitfalls in any data science or forecasting project. A vague or ill-defined goal can lead to irrelevant forecasts. You might accurately forecast something, but if it doesn't align with a decision or problem, the forecast is useless. Imagine forecasting the price of a stock when your actual goal was to predict overall market sentiment. Wasted effort and resources. Without a clear target, teams can spend significant time and money collecting irrelevant data, developing complex models that don't address the core need, or chasing elusive metrics. Scope creep. The project can endlessly expand as new, loosely related questions arise, derailing progress and delaying completion. Difficulty in evaluation. If you don't know what success looks like from the outset, it's impossible to objectively evaluate the performance and value of your forecasting model. Project failure. Ultimately, a lack of direction can lead to projects being abandoned or failing to deliver any meaningful impact. How the goal shapes the forecast type. Your defined goal directly influences the type of forecast you need to produce. Different goals require different outputs. Point forecast versus probabilistic forecast. If your goal is to know the most likely single value, e.g., what will be the exact temperature tomorrow, you need a point forecast. If your goal involves understanding uncertainty and risk, e.g., what is the probability that the temperature will drop below freezing tomorrow, or what range of temperatures is most likely, you need a probabilistic forecast. AST, e.g., prediction intervals or full probability distributions. This is crucial for risk management or setting safety stock levels. Short-term versus long-term forecast. A goal like optimize staffing for tomorrow's call center volume requires a short-term forecast, hourly, daily. A goal like plan capital expenditure for new factory capacity over the next 5 years requires a long-term forecast, yearly. The methods and data used for these will differ significantly. Univariate versus multivariate forecast. If your goal is simply predict the future value of a single variable, e.g., how much electricity will be consumed next hour, you might need a univariate forecast. If your goal requires understanding the relationship and future values of multiple interdependent variables, e.g., predict sales of product A and product B simultaneously, considering their cross-promotions, you might need a multivariate forecast. Real-world applications. from personal decisions to business strategy. Let's solidify the connection between goal and forecast with examples. Personal scenario, the camping trip. Imagine your goal is to code snippet. This is a clear, actionable personal goal. To achieve this, you need to make a decision about what kind of sleeping bag to pack. This decision, in turn, depends on anticipating the conditions. Goal: sleep comfortably on the camping trip. Decision informed by forecast: which sleeping bag and other gear to pack. Need for forecast: to make the right decision, you need to know the anticipated overnight temperature. Therefore, you need a temperature forecast. Type of forecast: a point forecast of the minimum overnight temperature, perhaps with a range, probabilistic forecast, to account for uncertainty for the specific location and dates of your trip. Impact: packing the right gear ensures comfort and safety, achieving the goal. This simple example illustrates how a personal comfort goal directly translates into the need for a specific type of forecast. Business scenario: retail inventory optimization. Now let's consider a business context. A large retail company faces challenges with inventory. Either too much stock leading to high holding costs and waste, or too little stock leading to lost sales and customer dissatisfaction. Goal: code snippet. This is a specific, measurable, and relevant business goal. Decision informed by forecast: how much of each product to order from suppliers and when. Need for forecast: to make informed ordering decisions, the company needs to anticipate future customer demand for each product. Therefore, they need a product demand forecast. Type of forecast: this would likely involve thousands of individual point forecasts, e.g., daily sales units per SKU, for a short to medium-term horizon, e.g., next 1 to 3 months, potentially with probabilistic forecasts, prediction intervals, to manage stock-out risk. It might also involve multivariate forecasts if demand for certain products is interdependent or influenced by shared factors like promotions. Impact: accurate demand forecasts enable the company to order just enough stock, reducing excess inventory costs, minimizing waste, and preventing lost sales due to stockouts, directly contributing to the goal and improving profitability. In both examples, the initial goal-setting phase is paramount. It serves as the guiding star, ensuring that all subsequent data collection, model development, and evaluation efforts are aligned with delivering tangible value and solving a real-world problem. This foundational step is what transforms raw data and complex algorithms into actionable intelligence. 1.2.2 Determining what must be forecast to achieve your goal. After establishing a clear and actionable goal for your forecasting project, the next critical step is to translate that high-level objective into a precise, quantifiable variable that needs to be predicted. This step acts as the crucial bridge between an abstract business need and the concrete data science task. It dictates what data you will collect, what models you might use, and ultimately, how you will measure the success of your forecast. The translation process, from goal to forecast target. Defining what must be forecast involves a process of decomposition and specificity. You start with your overarching goal and then ask, what specific, measurable future value or event, if known, would directly enable me to achieve this goal? Consider the following thought process. 1. Analyze the goal. Revisit your goal and identify the core uncertainty that prevents you from achieving it. 2. Identify the unknown. Pinpoint the specific piece of information that, if you had it for the future, would resolve that uncertainty. 3. Quantify the unknown. Can this unknown be expressed as a number, a category, or a specific value? If not, how can it be made measurable? 4. Define granularity and horizon. Over what time period, e.g., hourly, daily, weekly, monthly, and how far into the future, e.g., next hour, next quarter. Do you need this forecast? This step is paramount because it ensures that your efforts in data collection, model development, and analysis are focused and aligned with the project's ultimate purpose. Without a clearly defined forecast target, you risk collecting irrelevant data, building models that don't address the core problem, or failing to deliver a valuable solution. Impact on downstream project phases. The variable you choose to forecast has far-reaching implications across your entire forecasting project roadmap. Data collection. The forecast target directly determines what historical data you need to gather. If you decide to forecast code snippet, you will need historical records of code snippet. If you switch to code snippet, your data aggregation strategy changes. Similarly, potential exogenous variables, features that might influence your target, are also guided by the nature of the target variable. Feature engineering. The characteristics of your forecast target influence the types of features you might engineer. For example, if forecasting code snippet, features related to customer interaction frequency, service usage, or past complaints become highly relevant. Model selection. The nature of the variable, continuous, categorical, count data, will guide your choice of forecasting models. Forecasting a continuous variable like code snippet might lead you to regression models, while forecasting code snippet, count data, might suggest Poisson regression or specific time series models for count data. Evaluation metrics. How you measure the accuracy and utility of your forecast is entirely dependent on what you are forecasting. For code snippet, metrics like mean absolute error, MSE, or root mean squared error, RMSE, are common. For code snippet, e.g., predicting if a customer will churn, metrics like accuracy, precision, or recall would be used. Real-world examples of defining forecast targets. Let's explore several practical scenarios to solidify your understanding of this crucial translation process. Example 1. The comfortable camping trip. High-level goal. Have a comfortable and enjoyable camping trip this weekend. Core uncertainty. What weather conditions will be present, especially overnight? What must be forecast? To be comfortable, you need to pack appropriate sleeping gear. The most critical factor for sleeping comfort is typically the code snippet. While code snippet is also important for comfort related to warmth, code snippet is the direct driver for packing decisions, e.g., sleeping bag rating, extra blankets. Forecast target. Code snippet for the specific location and dates of the trip. Implication. You would seek historical temperature data and potentially other weather variables like humidity or wind chill to build a model that predicts this specific temperature. Example 2. Inventory management and stockouts. High-level goal. Reduce stockouts for product X at our main distribution center, ensuring product availability for customers. Core uncertainty. How much of product X will customers buy or demand? In the coming period? What must be forecast? To prevent stockouts, you need to know how much product to have on hand. This directly relates to code snippet. The granularity matters. Code snippet, or code snippet for product X, depending on lead times and ordering frequency. Forecast target, code snippet for product X. Implication. Your model would consume historical sales data for product X, potentially incorporating factors like promotions, seasonality, or competitor actions to predict future demand. This forecast then directly informs purchasing and inventory replenishment decisions. Example 3. Optimizing customer support staffing. High-level goal. Optimize staffing levels for the customer support team to minimize customer wait times while controlling operational costs. Core uncertainty. How many customer inquiries will arrive at any given time? What must be forecast? To staff appropriately, you need to anticipate the incoming workload. This workload is best represented by the code snippet or code snippet. The granularity here is often quite fine-grained, such as code snippet or even code snippet, to allow for dynamic staffing adjustments. Forecast target, code snippet per hour/interval. Implication. Your model would analyze historical ticket volumes, considering factors like time of day of week, marketing campaigns, or product launches to predict future call/ticket volumes. This forecast directly guides workforce management systems for SCH. Edgeling agents. Addressing complexities and pitfalls. While the concept of identifying a single forecast target seems straightforward, real-world scenarios can present challenges. Multiple forecast targets for a single goal. Sometimes, a single overarching goal requires forecasts of multiple interdependent variables. For instance, optimizing a complex supply chain might require forecasting code snippet, and code snippet simultaneously. In such cases, each of these becomes a distinct forecasting task, potentially leading to multiple models or a multi-output model. Non-obvious targets or proxy variables. The most direct variable might not always be the easiest or even possible to forecast directly. You might need to forecast a proxy variable that correlates strongly with your actual interest. For example, if you want to forecast code snippet, which is hard to quantify directly and immediately, you might instead forecast code snippet or code snippet as proxies. Avoiding forecasting everything. A common pitfall is to try and forecast too many things, or to forecast a variable that is only tangentially related to the goal. This leads to wasted effort, diluted focus, and models that don't provide clear business value. Always return to the question, what must I know to achieve this specific goal? Best practices for target identification. Be specific and quantifiable. Ensure the variable is measurable and has clear units, e.g., units sold, degrees Celsius. Number of calls. Avoid vague terms. Align with business action. The forecast should directly inform a decision or action. If knowing the forecast doesn't change what you do, it might not be the right target. Consider granularity and horizon. Define the time scale, hourly, daily, weekly, and the forecast horizon, how far into the future, that are most relevant to the decision-making process. Forecasting code snippet is useless if you need to optimize code snippet. Iterate if necessary. It's possible that after some initial data exploration or model building, you realize your chosen forecast target isn't quite right. Be prepared to revisit and refine it based on new insights. By meticulously defining what needs to be forecast, you lay a solid foundation for the subsequent steps in your forecasting project, ensuring that your efforts are efficient, relevant, and ultimately successful. Setting the horizon of the forecast. The previous steps established the overarching goal of your forecasting project and precisely identified the specific variable to be predicted. The next critical step is to define the forecast horizon. This term refers to the specific future period for which you need predictions. It's not merely a duration. It encompasses both the code snippet and the code snippet of the forecast period. What is the forecast horizon? Formally, the forecast horizon is the future time interval for which a time series model will generate predictions. It is defined by two key components. 1. Forecast start time. This is the precise point in time immediately following the last known observation of your time series data. If your last recorded sales figure is for December 31st, 2023, and you want to forecast for January 2024, your forecast start time is effectively January 1st, 2024. 2. Forecast duration. This is the length of the period into the future for which predictions are required. It could be an hour, a day, a week, a month, a quarter, or even several years. Consider a scenario where you've collected daily sales data up to the end of last month, say October 31st, 2023. You now need to predict sales for the entire upcoming month of November 2023. Download the code on one patch code Substack. In this example, the code snippet marks the beginning of the future period we are interested in. The code snippet specifies how long into the future we need to predict CU. Culminating at the code snippet. This combination of start and duration defines the complete forecast horizon. Types of forecast horizons. The manner in which the forecast horizon is managed over time is crucial and typically falls into two main categories: fixed horizon and rolling horizon. Fixed horizon forecast. A fixed horizon forecast refers to a scenario where predictions are made for a specific, unchanging future period. Once the forecast is generated, it remains valid for that defined period, regardless of new data becoming available. This approach is common for strategic planning or one-off events. Characteristics. A single forecast is produced for a predetermined future interval. The forecast period does not shift as new data arrives. Often used for long-term planning, budget setting, or project milestones. Example: predicting annual revenue for the next fiscal year, e.g., 2025, based on data up to the end of 2024. Once the forecast for 2025 is made, it's used for the entire year, even as Q1 2025 actuals come in. Download the code on OnePatchCode Substack. This approach is straightforward for static planning, but it means the forecast doesn't update with the latest information. Rolling Horizon Forecast. A rolling horizon forecast, also known as a dynamic or moving horizon, involves continually updating the forecast as new data becomes available. With each new data point or period, the forecast window rolls forward, dropping the oldest predicted period and adding a new future period. Characteristics. Forecasts are regularly regenerated based on the most recent data. The forecast window moves forward in time, maintaining a consistent future duration. Ideal for operational planning, inventory management, and situations requiring continuous adjustments. Example: forecasting daily electricity demand for the next 7 days. Every day, as actual demand for the current day becomes known, the forecast is rerun to predict demand for the next 7 days, effectively dropping the oldest day from the forecast window and adding a new future day. Download the code on OnePatchCode Substack. As shown, the forecast window shifts forward, always looking 7 days into the future from the latest available data. This dynamic nature allows for more responsive decision-making. The strategic importance of the forecast horizon. Defining the forecast horizon is far more than just picking a future date. It is a strategic decision that fundamentally impacts every subsequent step of your forecasting project. Impact on data requirements. The forecast horizon dictates the type, quantity, and frequency of historical data you need. Quantity. A longer forecast horizon generally requires a longer historical data series to capture underlying trends, seasonality, and cycles. If you need to forecast 5 years into the future, having only 6 months of historical data is insufficient. Frequency. The granularity of your historical data should ideally match or be finer and your forecast horizon's granularity. If you need to forecast daily sales, your historical data should be daily or sub-daily. Forecasting monthly sales from only annual data is challenging. External data. For longer horizons, external factors become increasingly important. Predicting next week's sales might primarily rely on past sales, but forecasting next year's sales might require macroeconomic indicators, GDP, inflation, competitor data, or policy changes. Impact on model selection. Different forecasting models are inherently better suited for different forecast horizons. Short-term forecasts, e.g., next hour, next day, next week models that capture recent patterns, high-frequency seasonality, and short-term trends are preferred. Examples include ARIMA/SARIMA, exponential smoothing, ETS, or simple machine learning models, e.g., random forest, gradient boosting, on lag features. These models often rely heavily on the immediate past. Medium-term forecasts, e.g., next month, next quarter models that can capture more complex seasonality, e.g., yearly patterns, trends over longer periods, and the influence of specific events are suitable. Profit, more advanced statistical models, or deep learning models, e.g., LSTMs, can be effective. Long-term forecasts, e.g., next year, next 5 years. These forecasts are less about precise point predictions and more about capturing macro trends, structural changes, and strategic direction. Statistical models might struggle with long-term nonlinearities. Causal models, scenario planning, or advanced machine learning/deep learning approaches incorporating a wide range of exogenous variables are often considered. The further out you forecast, the more the forecast becomes about capturing underlying drivers rather than extrapolating past patterns. Impact on evaluation metrics. The choice of forecast horizon also influences which evaluation metrics are most appropriate to assess model performance. Short-term, absolute error metrics like mean absolute error, ME, or root mean squared error, RMSE, are often suitable as the magnitude of error is directly interpretable and consistent across the short horizon. Long-term, percentage-based errors like mean absolute percentage error, MAPE, or symmetric mean absolute percentage error, SMAPE, can be more useful, especially if the scale of the time series can vary significantly over a long period. A fixed absolute error might be small for large values but devastating for small values. Percentage errors normalize this. For very long horizons, directional accuracy or capturing turning points might be more important than precise point estimates. Common horizon categories and domain examples. Forecast horizons are often categorized broadly, though the exact duration for each category can vary significantly depending on the domain and the frequency of the time series data. The key is often the number of steps into the future rather than the absolute time. Horizon category typical duration, examples, domain examples, and use cases. Download the code on one Pagecode Substack. This initial code snippet sets up a foundational understanding of generating time series data. We establish a synthetic dataset representing historical observations, crucial for any forecasting endeavor. The code snippet function creates a data frame with a code snippet column and a code snippet, simulating a typical time series structure. Download the code on one Pagecode Substack. This segment illustrates how different forecast horizons, short, medium, long, are conceptualized relative to the code snippet. Notice how we use code snippet to define these future points, demonstrating the direct impact of the horizon on the future period we aim to predict. Interplay with data frequency. It's critical to understand that the terms short-term, medium-term, and long-term are relative to the frequency of your time series data. A short-term forecast for hourly data, e.g., predicting the next 24 hours, involves 24 forecast steps. A short-term forecast for annual data, e.g., predicting the next 2 years, involves only 2 forecast steps, yet covers a much longer absolute time duration. The number of forecast steps often has a more direct impact on model complexity and performance than the absolute time duration. For instance, forecasting 30 days of daily data, 30 steps, is very different from forecasting 30 years of annual data, 30 steps, even though the number of steps is the same. The underlying patterns and external influences will vary significantly. Understanding and clearly defining the forecast horizon is a foundational step that sets the stage for data preparation, model selection, and the ultimate evaluation of your forecasting solution. A well-defined horizon ensures that the entire project is aligned with the business or operational goal it aims to support. Gathering the data. Once you have clearly defined your forecasting goal, identified the target variable, and set the forecast horizon, the next critical step is to gather the necessary historical data. This data serves as the foundation upon which your forecasting models will be built, trained, and validated. Without sufficient, relevant, and quality data, even the most sophisticated models will yield unreliable results. Identifying relevant data. The first aspect of data gathering involves identifying precisely what data you need. This typically falls into 2 categories. 1. Target variable data. This is the historical record of the variable you intend to forecast. If your goal is to forecast daily sales, you need historical daily sales figures. If you're forecasting hourly temperature, you need historical hourly temperature readings. This time series must align with the frequency and scope of your forecast horizon. 2. Exogenous variables. Predictor variables. These are external factors that are not directly being forecast, but are believed to influence the target variable. Including relevant exogenous variables can significantly improve forecast accuracy by providing additional context and explanatory power to your model. For example, if you're forecasting daily sales, target variable, daily sales amount. Potential exogenous variables. Promotional activities. Was there a discount, a marketing campaign, or a special event on that day? Holidays. Was it a public holy day, a national holiday, or a school holiday? Weather. Did extreme weather, e.g., a snowstorm, heat wave occur? Competitor actions. Did a major competitor launch a new product or promotion? Economic indicators. Are there relevant economic indices, e.g., consumer confidence, unemployment rates, that might impact sales? The selection of exogenous variables requires domain knowledge and careful consideration. Not all related variables are useful. Some might be redundant, or their relationship with the target variable might be too complex or nonlinear to capture effectively with simpler models. It's often an iterative process of adding and removing variables based on model performance. How much data is enough? A common question in time series forecasting is, how much historical data do I need? There isn't a single universal answer, as the optimal quantity depends on several factors. Forecast frequency. If you are forecasting hourly data, a month's worth of data contains 2430 is equal to 720 data points. If you are forecasting monthly data, a year's worth contains only 12 data points. Higher frequency data generally requires a longer history in terms of number of observations, even if the duration is shorter. Seasonal patterns. If your data exhibits seasonality, e.g., daily, weekly, monthly, yearly cycles, you ideally need enough historical data to capture multiple cycles of each significant seasonal pattern. For yearly seasonality, you should aim for at least 3 to 5 years of D. Added to allow the model to learn the annual patterns consistently and distinguish them from random fluctuations or trends. For weekly seasonality, e.g., higher sales on weekends, you'd want several months of daily data to capture these weekly cycles repeatedly. Pitfall. If you only have 1 year of data for a yearly seasonal series, the model might struggle to differentiate true seasonality from a unique event that occurred in that specific year. Trend. To accurately identify and model long-term trends, you need a sufficiently long time series that spans the period over which the trend has been developing. Short data series might show a misleading trend or no trend at all. Model complexity. More complex models, particularly those based on machine learning or deep learning, often require larger datasets to learn intricate patterns and generalize well, reducing the risk of overfitting. Data availability and practical constraints. Sometimes, the amount of data you can gather is limited by its availability, storage costs, or the computational resources required to process it. While more data often leads to better models, there's a point of diminishing returns where the marginal benefit of adding more data is outweighed by the increased computational cost and processing time. For example, processing terabytes of historical data can be incredibly time-consuming and resource-intensive, even if it theoretically offers a slight accuracy improvement. Ultimately, determining the optimal data quantity is often an empirical process involving experimentation. You might start with a reasonable amount of data, build a model, and then test if adding more historical data improves performance significantly. Methods and tools for data acquisition. Data can reside in various places and formats. Understanding how to access and load this data into a usable format, typically a pandas data frame in Python, is a fundamental skill. Common data formats. Time series data is frequently stored in formats that facilitate easy storage and retrieval. CSV, comma-separated values, a very common and simple text-based format where values are separated by commas. Easy to read and write, but lacks schema information. Excel, XLSX, XLS spreadsheet formats often used for smaller datasets or manual data entry. Parquet, a columnar storage format that is highly efficient for large datasets, especially within big data ecosystems. It's optimized for analytical queries. JSON, JavaScript object notation, a lightweight data interchange format, often used for data transfer via APIs. Databases, SQL, NoSQL data stored in structured tables, e.g., PostgreSQL, MySQL, SQL Server, or more flexible document-based systems, e.g., MongoDB, Cassandra. Python libraries for data loading. Python offers robust libraries to handle data acquisition from various sources. Code snippet is the cornerstone for data manipulation and is excellent for loading structured data. Loading data from CSV. Files. CSV files are perhaps the most common way to share and store time series data due to their simplicity. Download the code on one PageCode Substack. This first step prepares our environment by simulating a code snippet file, and then uses code snippet to load it. The code snippet argument is vital as it automatically converts the specified columns into datetime objects, which are essential for time series analysis. Setting code snippet makes the date column the data frame's index, enabling time-based operations like resampling and slicing. Initial data inspection. After loading, it's crucial to perform an initial inspection to understand the data structure, identify potential issues, and confirm that the loading process was successful. Download the code on OnePageCode Substack. Code Snippet provides a quick glance at the top rows, allowing you to confirm column names and initial data values. Code Snippet is invaluable as it shows the data types of each column and the count of non-null values. For time series, ensuring your time index is a code snippet type and your target variable is a numeric type is paramount. Basic data quality checks. Even at this early stage, it's good practice to perform some basic quality checks, even if full data cleaning is a later step. Download the code on OnePageCode Substack. Code Snippet quickly tallies missing values per column, giving you an immediate sense of data completeness. Code Snippet checks for duplicate timestamps, which can be problematic for time series models, assuming a unique time step. Finally, verifying the data's time range helps ensure you've loaded the correct historical period. Visualizing the time series. A simple plot of the time series is often the best first step to visually detect trends, seasonality, outliers, or gaps. Download the code on OnePageCode Substack. This plot serves as a fundamental diagnostic tool. You can quickly spot obvious trends, upward/downward slope, seasonality, repeating patterns, or unusual spikes/dips that might indicate outliers or special events. This visual inspection guides further data processing and model selection. Other data sources and tools. Brief mentions. Databases. For data stored in SQL databases, e.g., PostgreSQL, MySQL, SQL Server, libraries like Code Snippet combined with Code Snippet are powerful. Download the code on OnePageCode Substack. APIs, application programming interfaces. Many online services, financial data providers, weather services, social media platforms, offer APIs to programmatically access data. The Code Snippet library is commonly used for this. Download the code on OnePageCode Substack. Web scraping. For data available on websites, but without a formal API, libraries like Code Snippet or Code Snippet can be used to extract information. This method is generally more complex and less robust due to website structure changes. Initial considerations for data quality. While comprehensive data cleaning is a dedicated step later in the forecasting roadmap, it's crucial to have a conceptual understanding of data quality even during acquisition. Poor data quality can lead to biased models and inaccurate forecasts. Missing values. Data gaps are common. Decide whether to fill, impute them, remove the rows/columns, or use models that can handle missingness. Outliers. Extreme values that deviate significantly from the rest of the data. They can be legitimate events or errors. Identifying and understanding them is important, as they can disproportionately influence model training. Data types and consistency. Ensure columns are the correct data type, e.g., numbers as numeric, dates as datetime objects. Check for consistent units, e.g., all sales in USD, all temperatures in Celsius. Frequency and alignment. Confirm that the data frequency matches your needs, e.g., daily sales, not weekly. If combining multiple series, ensure their time indices align correctly. By carefully gathering and performing initial checks on your data, you lay a strong foundation for the subsequent steps of exploratory data analysis, feature engineering, and model building. Developing a forecasting model. Once you have meticulously gathered and prepared your time series data, the next pivotal step in your forecasting project is to develop a robust forecasting model. This stage involves a careful selection of appropriate models based on your data's unique characteristics, followed by rigorous evaluation to ensure the chosen model performs optimally for your specific forecasting objective. 2.1 Model Selection Strategy. Matching models to data characteristics. The journey to an effective forecasting model begins with a deep understanding of your data. The characteristics of your time series, such as the presence of trends, seasonality, and the influence of external factors, exogenous variables, are paramount in guiding your model selection. This is where the exploratory data analysis, EDA, and time series decomposition, discussed in earlier sections, become invaluable. 2.1.1 Reevaluating data characteristics. Before diving into model choices, revisit your data's inherent patterns. Trend. Does your data show a long-term increase or decrease? Seasonality. Are there occurring patterns at fixed intervals, e.g., daily, weekly, monthly, yearly? Cycles. Are there longer-term patterns that are not fixed in length? Exogenous variables. Do external factors, not part of the time series itself, influence its behavior, e.g., holiday promotions affecting sales, temperature affecting electricity consumption? Data volume. How much historical data do you have? This significantly impacts the feasibility of certain model types. While visual inspection through line plots and decomposition plots, as discussed in section 1.2.3, analyzing time series components, provides a strong initial understanding, more formal methods can confirm these observations. Statistical tests like the augmented Dickey-Fuller (ADF) test can help determine if a trend is present, i.e., if the series is non-stationary and needs differencing. An autocorrelation function, ACF, and partial autocorrelation function, PACF, plots are excellent tools for identifying seasonal patterns in the order of autoregressive, AR, and moving average, MA components. 2.1.2 Categories of forecasting models. Forecasting models broadly fall into two main categories: statistical learning models and deep learning models. Each has its strengths, weaknesses, and ideal use cases. Statistical learning models. These models are often based on well-established statistical principles and assumptions about the data generation process. They are generally more interpretable, meaning it's easier to understand how they arrive at their predictions. Examples: ARIMA, autoregressive integrated moving average; SARIMA, seasonal ARIMA; SARIMAX, seasonal ARIMA with exogenous variables; exponential smoothing models, e.g., Holt-Winters. Strengths: good performance on smaller to medium datasets, strong interpretability, robust for many common time series patterns. Weaknesses: can struggle with highly complex, nonlinear patterns, may require more feature engineering for exogenous variables. Deep learning models, a subset of machine learning models inspired by the structure and function of a human brain's neural networks. These models excel at learning complex, nonlinear relationships directly from data. Examples: recurrent neural networks, RNNs, like LSTMs, long short-term memory; and GRUs, gated recurrent units; convolutional neural networks, CNNs, adapted for sequence data; transformers. Strengths: exceptional performance on very large datasets, ability to capture intricate nonlinear dependencies, less reliance on explicit feature engineering for complex interactions. Weaknesses: require substantial amounts of data for optimal performance, computationally intensive to train, often less interpretable black box models, prone to overfitting if not properly regularized. The choice between these categories often comes down to data volume and complexity. For simpler, smaller datasets with clear trends and seasonality, statistical models are often sufficient and more efficient. For massive datasets with highly complex, nonlinear interactions, deep learning models can unlock superior predictive power. 2.1.3 Common Time Series Forecasting Models. Conceptual Overview. Let's briefly touch upon some common models you'll encounter, understanding that detailed explanations are reserved for later chapters. SARIMA, Seasonal Autoregressive Integrated Movement. G-Average. Concept: an extension of the ARIMA model that explicitly handles seasonality. It uses seasonal differencing to remove seasonal trends and applies seasonal autoregressive, SAR, and seasonal moving average, SMA, components to model seasonal dependencies. How it leverages seasonality. SARIMA models seasonality by applying ARIMA components not just to the current observation in recent past, but also to observations from previous seasons, e.g., the same month last year. This allows it to capture repeating patterns that occur over a fixed period. Applicability. Ideal for time series with clear trend and seasonal patterns, but no significant external influencing factors. Ceramax, seasonal autoregressive integrated moving average with exogenous variables. Concept. Builds upon Sarima by incorporating additional independent variables, exogenous variables, into the model. These variables are not part of the time series you're forecasting, but are believed to influence it. How it leverages exogenous variables. Ceramax directly includes these external variables as predictors in the model, allowing it to account for their impact on the forecast target. For instance, forecasting ice cream sales might benefit from including temperature as an exogenous variable. Applicability. When external factors demonstrably impact your time series, Ceramax offers a way to explicitly model their influence alongside trend and seasonality. Neural networks, e.g., LSTMs. Concept, a P of deep learning model particularly well suited for sequence data like time series. LSTMs are designed to remember information for long periods, which is crucial for capturing long-term dependencies in time series data. How they learn complex patterns. Unlike statistical models that rely on predefined structures, like AR or MA components, neural networks learn hierarchical representations of the data through multiple layers of nonlinear transformations. This allows them to automatically discover intricate, nonlinear relationships and interactions between variables that might be missed by traditional methods. Why they need large data. Their ability to learn complex patterns comes at the cost of needing vast amounts of data to properly tune their many parameters and avoid overfitting. With insufficient data, they can easily learn noise instead of true patterns. Applicability. Excellent for very large, complex datasets with potentially nonlinear relationships, and when interpretability is less critical than raw predictive power. 2.2 Model Evaluation. Assessing forecast accuracy. Developing a model is only half the battle. The other half is rigorously evaluating its performance. A model's true worth is not in its complexity or theoretical elegance, but in its ability to generate accurate forecasts on unseen data. 2.2.1 The critical role of the test set in time series. In any machine learning project, a fundamental principle is to evaluate your model on data it has not seen during training. For time series, this principle is even more crucial and comes with a specific constraint. Temporal order must be preserved. Unlike typical machine learning problems where you might randomly split your data into training and test sets for time series, you must split your data chronologically. The training set consists of older data, and the test set consists of the most recent data. This simulates a real-world forecasting scenario where you use historical data to predict future values. The test set must be representative of the forecasting horizon, in the sense that its characteristics, e.g., seasonality, trend, should align with what you expect in the future period you intend to forecast. If your test set covers a period with unusual events, e.g., a major economic recession, that are unlikely to repeat in your actual forecasting horizon, your evaluation might be misleading. Let's illustrate a time series train test split with a Python example using code snippet. We'll simulate some time series data. Download the code on OnePageCode Substack. This initial code block sets up a synthetic time series dataset using code snippet and code snippet. We create a daily time series for a year, incorporating a linear trend, a seasonal sine wave pattern, and some random noise. This provides a realistic-looking dataset to demonstrate the train test split. Download the code on OnePageCode Substack. Here, we perform the critical chronological split. We calculate the code snippet as 80% of the total data length. Then, we use code snippet integer location-based indexing to slice the data frame. The first code snippet rows go into code snippet, and the remaining rows go into code snippet. This ensures that the test set always contains observations after the training set, mimicking real-world forecasting. An code snippet statement is included to programmatically confirm the chronological integrity of the split. 2.2.2 Common Error Metrics. After training a model on the code snippet and generating forecasts for the code snippet, you need metrics to quantify how well those forecasts align with the actual values. Mean squared error, MSE. Mean squared error, MSE, is one of the most widely used error metrics. It calculates the average of the squared differences between the predicted values and the actual values. Formula. $MSE in havali vrak vinvensimbi in havali infin I hakavi dui dollar. Where $$ is the actual value at time $I. $hat y is the predicted value at time $I. $& is the number of observations in the test set. Interpretation. MSE gives more weight to larger errors because the errors are squared. This means that models with even a few very large errors will have a significantly higher MSE. A lower MSE indicates a better fit. The unit of MSE is the square of the unit of the data, e.g., if you're forecasting temperature in Celsius, MSE is in Celsius squared. Let's walk through a simple numerical example for MSE calculation. Numeri. Cal example. Suppose we have the following actual values and predictions for a small test set. Actual values, $y code snippet. Predicted values, $hat, y code snippet. 1. Calculate differences. $10, 9 equals $1. $12, 13 equals negative $1. $11, 10.5 equals 50 cents. 2. Square differences. $1 2 equals $1. $, moins 1, 2 égale $1. $0.52 égale 25 cents. 3. Some square differences. $1 plus 1 plus 0.25 equals $2.25. 4. Calculate mean, divide by n equals 3. Cifrão MS é igual contra barra frac 2.25 e 3 igual $0.75. Now, let's implement this in Python. We'll simulate some predictions for our code snippet. Download the code on one Pagecode Substack. Before calculating MSE, we need actual values and corresponding predictions. Since we don't have a train model yet, this chunk simulates code snippet for the code snippet. In a real scenario, code snippet would be generated by your trained forecasting model. We align the actual values from code snippet with these predictions. Download the code on one Pagecode Substack. This final code block demonstrates two ways to calculate MSE, manually by applying the formula steps in Python and using code snippet's code snippet function. The code snippet function is generally preferred in practice due to its robustness and efficiency. We compare the results to ensure consistency. Other common error metrics. While MSE is widely used, it's often beneficial to consider other metrics, as each provides a slightly different perspective on model performance. Root mean squared error, RMSE. Formula, $RMSE equals $\sqrt$. Interpretation, RMSE is simply the square root of MSE. Its main advantage is that it's in the same units as the original time series, making it more interpretable than MSE. Like MSE, it penalizes large errors more heavily. Mean absolute error, MAE. Formula, $MAE in havali vrak vinvensimbi in havali infinvi hata $. Interpretation, MAE calculates the average of the absolute differences between predictions and actuals. It is less sensitive to outliers than MSE or RMSE because it doesn't square the errors. It provides a straightforward average magnitude of error in the same units as the data. Pros, easy to understand, robust to outliers. Cons, does not penalize large errors as much as MSE/RMSE, which might be undesirable if large errors are particularly costly. Mean absolute percentage error, MAPE. Formula, $MAP equals \frac, what the some I equals 1 in \left \frac, e \hat, y \right times 100 $. Interpretation. MAPE expresses the error as a percentage of the actual value. This makes it useful for comparing forecast accuracy across different time series or datasets that have different scales. Pros: scale independent, intuitive percentage interpretation. Cons: undefined or infinite when actual values, $, are 0. Can be unstable when actual values are very close to 0, leading to extremely large percentage errors, even for small absolute errors. It also implicitly assumes that an error of a certain percentage is equally important across all scales. When to prefer which metric? MSE/RMSE. When large errors are particularly undesirable and you want your model to be heavily penalized for them, e.g., financial forecasting where large errors can lead to significant losses. MID. When you want a robust measure of average error magnitude, less influenced by outliers, and interpretability in the original units is key. MAPE. When you need a scale-independent metric to compare performance across different datasets, or when errors are best understood as percentages of the actual values, e.g., sales forecasting. Be cautious with values near 0. 2.2.3 Comparative analysis and model selection. After evaluating multiple candidate models using one or more error metrics, you'll need to compare their performance. The model with the lowest error on the test set is generally considered the best model for your specific problem and data. However, selection isn't always solely based on the lowest error metric. Other factors include interpretability. Can you understand why the model makes certain predictions? Statistical models often offer higher interpretability. Computational cost. How long does it take to train and make predictions? Deep learning models can be very resource-intensive. Robustness. How well does the model perform under slight variations or noise in the data? Ease of maintenance/deployment. How simple is it to update the model with new data or integrate it into existing systems? It's often a trade-off. A slightly less accurate but much more interpretable or computationally efficient model might be preferred over a marginally more accurate but opaque and complex one, especially in business contexts where understanding and trust are critical. 2.2.4 Beyond single train test splits. Walk-forward validation. While a single train test split is a good starting point, it only provides one snapshot of performance. For more robust evaluation, especially with limited data or when dealing with evolving time series, walk-forward validation, also known as rolling forecast origin, is a superior strategy. In walk-forward validation, 1. You train your model on an initial segment of the time series. 2. You forecast for the next immediate period, e.g., the next day or week. 3. You then walk forward by adding the actual observed value for that period to your training data. 4. You retrain the model or update it and forecast the next period. This process repeats, simulating a real-time forecasting scenario and providing a more reliable estimate of model performance over various historical periods. While more computationally intensive, it offers a much richer understanding of your model's stability and generalization ability. Deploying to production. Once a champion forecasting model has been developed and thoroughly validated, the next crucial step is to deploy it to a production environment. This transition marks the shift from an experimental, development-focused phase to making the model operational and accessible for practical use. Deploying a model means making it available for automated predictions without requiring manual intervention, allowing it to seamlessly integrate into existing business processes or applications. The ultimate goal of deployment is to enable the model to consistently take in new data and return predictions, serving a specific business need or end-user application. This automation ensures that forecasts are generated reliably, consistently, and at scale, transforming insights from the model into actionable intelligence. Deployment paradigms. Batch versus real-time inference. The choice of deployment strategy heavily depends on how and when predictions are needed. We typically differentiate between two primary paradigms: batch inference and real-time, or online inference. Batch inference. Batch inference involves making predictions on a large collection of data points at once, typically on a scheduled basis. The model processes the entire batch, and the generated forecasts are then stored or delivered for later use. Characteristics. Latency. High latency is acceptable, as predictions are not needed instantaneously. Throughput focuses on processing large volumes of data efficiently. Use cases: nightly sales forecasts, monthly budget projections, weekly inventory reordering, or any scenario where predictions can be pre-calculated. Example use case: a retail company generating sales forecast for the next quarter on a weekly basis. The model runs on a server, processes historical sales data along with any new relevant information, e.g., marketing campaigns, and then updates a database with the projected sales figures. Business analysts or dashboards then pull these pre-calculated forecasts. Real-time, online, inference. Real-time inference involves making predictions on individual data points as they arrive, providing forecasts almost instantaneously. This requires the model to be constantly running and ready to receive new inputs. Characteristics. Latency. Low latency is critical, as predictions are needed immediately. Throughput focuses on handling individual requests rapidly. Use cases: predicting demand for a ride-sharing service as a new request comes in, recommending products to a user browsing an e-commerce site, or real-time fraud detection. Example use case: a weather application that displays temperature forecasts for a specific location. When a user requests the forecast, the application sends the location data to a deployed model, which then returns the prediction instantly to be displayed to the user. Common model deployment approaches. The method of deployment chosen depends on the specific requirements of the application, the existing infrastructure, and the scale of operations. 1. Model as an API, application programming interface. One of the most common and flexible ways to deploy a forecasting model is by exposing it as a RESTful API. This allows other applications, web applications, mobile apps, internal systems, dashboards, to send data to the model and receive predictions back programmatically. Advantages: interoperability, language and platform agnostic, allowing diverse systems to consume predictions. Scalability, can be scaled independently of the consuming applications. Modularity, encapsulates the model's logic, making it easier to update or replace. Conceptual flow. A client application sends a request, e.g., HTTP post, with input data to a specific API endpoint. A server hosts the model, processes the input using the model, and returns the prediction in a structured format, e.g., JSON. Let's illustrate with a minimal Python example using Code Snippet, a micro-web framework, to serve a dummy forecasting model. In a real-world scenario, your trained model, e.g., a code snippet model or code snippet model, will be loaded from a file. First, we need a dummy model and some dummy data to simulate a forecasting scenario. We'll use Code Snippet for a simple linear regression model as a placeholder for a time series model, as the focus here is on the deployment mechanism. Download the code on one patch code Substack. This initial code segment simulates the crucial step of having a trained model ready for deployment. We create a simple code snippet model, train it on some dummy data, and then save it to a file using Code Snippet. In a real forecasting project, Code Snippet would be your actual time series model, e.g., a code snippet model, code snippet, or a custom deep learning model that you spend time developing and validating. Saving it allows the deployment environment to load it without retraining. Next, we'll set up a code snippet application to serve this model via a REST API. Download the code on one patch code Substack. This part of the code initializes our Flask application and, critically, loads the pre-trained model into memory. Loading the model once when the application starts is a best practice for efficiency, as it avoids the overhead of loading it for every incoming prediction request. Error handling for model loading is also included to make the setup more robust. Now, we define the API endpoint that will receive data and return predictions. Download the code on one patch code Substack. This is the core of our API. The code snippet decorator registers the code snippet function to handle code snippet requests to the code snippet URL path. Inside the function, It retrieves JSON data from the incoming request, validates it, prepares the data in the format expected by the code snippet model, a 2D array, makes the prediction, and then returns the forecast as a JSON response. Robust error handling is included to manage cases of missing models, malformed input, or prediction failures. Finally, we add the code to run the Flask application. Download the code on one patch code Substack. This final chunk ensures that the Flask application runs when the script is executed directly. In a production environment, you would typically use a more robust WSGI, Web Server Gateway Interface, server like Unicorn or UWSGI to run your Flask application, which provides better performance, stability, and process management. The code snippet setting makes the server accessible from external machines on the network, which is necessary for deployment beyond your local machine. To test this API, you could send a post request using code snippet or a tool like Postman. Download the code on one patch code Substack. This would return a JSON response similar to code snippet. The exact value depends on your dummy model's training. 2. Batch processing via scheduled jobs. For batch inference, models are often deployed as part of a scheduled job or pipeline. This involves a script that runs periodically, loads the model, fetches new data, generates forecasts, and then stores or distributes these forecasts. Advantages. Simplicity. Can be simpler to set up than real-time APIs for non-interactive needs. Resource efficiency. Resources are only consumed during the scheduled run. Scalability. Can process very large datasets by leveraging distributed computing frameworks, e.g., Apache Spark. Conceptual flow. A scheduler, E.G. Cron on Linux, Windows Task Scheduler, Airflow, Prefect, triggers a Python script. The script connects to a data source, loads the model, makes predictions, and writes the results to a database, file, or sends them as a report. Here's a simplified Python script that simulates a batch forecasting process. Download the code on one patch code Substack. This initial part sets up configuration variables and simulates the arrival of new data that needs forecasting. In a production environment, code snippet might be a table in a data warehouse or a stream of events. We generate a few random input features and associate them with timestamps. Then save this to a CSV file to simulate new data. Next, the script will load the model and the new data, perform predictions, and save the results. Download the code on one patch code Substack. Here, the script loads the pre-trained model and the newly arrived data. It includes basic error handling for code snippet and other exceptions. The code snippet are extracted, ensuring they are in the correct format, e.g., a number py array for the model's code snippet method. Finally, the predictions are made and saved. Download the code on one patch code Substack. This section executes the code snippet method of the loaded model on the new data. The resulting code snippet are then added as a new column to the code snippet data frame, and the entire data frame, now including the forecasts, is saved to a new CSV file. In a production setting, this output might be written to a database table, a data lake, or sent to a reporting tool. This script would then be scheduled to run at regular intervals. 3. Integration into web applications or dashboards. While often leveraging an API backend, a forecasting model can also be directly integrated into a user-facing web application or business intelligence dashboard. This provides a graphical interface for users to input data, visualize forecasts, or interact with the model's output. Conceptual flow. A user interacts with a dashboard. Behind the scenes, the dashboard's backend either directly loads and runs the model, less common for large models, or, more typically, calls a dedicated model API, as described above, to retrieve forecasts. The results are then rendered visually for the user. 4. Embeddable models, e.g., Excel functions, edge devices. In some specialized cases, models might be converted into formats that can be embedded directly into applications or devices that traditionally don't host complex machine learning environments. This aligns with the professor's mention of Excel functions. Excel/spreadsheets, tools like ONNX, Open Neural Network Exchange, or PMML Predictive model markup language. Allow models trained in various frameworks to be exported into a portable format that can then be imported and run within applications like Excel, often via specific add-ins or custom functions. This allows business users to interact with a model directly in their familiar environment. Edge devices. For IoT, Internet of Things applications, models might be optimized and deployed directly onto small, low-power devices, e.g., smart sensors, to make real-time predictions without needing to send data back to a central server. This is common for predictive maintenance on machinery or localized weather predictions. Key considerations for production deployment. Deploying a model to production involves more than just making predictions. Several critical factors must be addressed to ensure the system is robust, reliable, and performs well under real-world conditions. Scalability. A production system must be able to handle varying loads, from a few requests per hour to thousands per second. Horizontal scaling. Adding more instances of the model service behind a load balancer to distribute incoming requests. Auto-scaling. Automatically adjusting the number of instances based on traffic load, common in cloud environments. Resource allocation. Ensuring sufficient CPU, memory, and GPU resources are available for the model to run efficiently. Latency. For real-time applications, the time it takes for a model to receive input, process it, and return a prediction, latency, is crucial. Optimization. Using optimized model formats, efficient code, and fast inference engines. Proximity. Deploying model services geographically closer to the users or data sources. Caching. Caching frequently requested forecasts or pre-computing predictions where possible. Reliability and high availability. Production systems must be resilient to failures and available around the clock. Redundancy. Deploying multiple instances of the model service across different servers or data centers. Load balancers. Distributing traffic and rerouting requests away from unhealthy instances. Failover mechanisms. Automated systems to switch to backup services in case of primary system failure. Fault tolerance. Designing the system to continue operating even if individual components fail. Security. Exposing a model via an API introduces security risks that must be mitigated. Authentication and authorization. Ensuring only authorized users or systems can access the model. This might involve API keys, OAuth tokens, or other identity management systems. Input validation. Sanitize and validate all incoming data to prevent injection attacks or unexpected model behavior due to malformed inputs. Data encryption. Encrypting data in transit, HTTPS, and at rest to protect sensitive information. Network security. Using firewalls, virtual private clouds, VPCs, and other network controls to restrict access. Version control and rollbacks. As models are continuously improved, managing different versions is essential. Model registry. A centralized repository for storing, versioning, and managing trained models. Deployment pipelines. Automated processes that allow for seamless deployment of new model versions and quick rollbacks to previous versions if issues arise. A/B. Testing/canary deployments. Gradually rolling out new model versions to a small subset of users to evaluate performance before full deployment. Monitoring. Brief introduction. While the next section will delve deeper into monitoring, it's critical to understand its importance immediately after deployment. Performance monitoring. Tracking the technical health of the deployed service, e.g., latency, error rates, resource utilization. Model performance monitoring. Crucially, tracking the accuracy and relevance of the model's predictions over time. This involves comparing forecasts against actual outcomes once they become available. Data drift. Monitoring changes in the characteristics of the input data compared to the data the model was trained on. Significant drift can degrade model performance. Concept drift. Monitoring changes in the relationship between input features and the target variable itself. This indicates that the underlying patterns the model learned are no longer valid. Introduction to MLOps, machine learning operations. The complexities of deploying, managing, and monitoring machine learning models in production have given rise to the discipline of MLOps. MLOps is a set of practices that combines machine learning, DevOps, and data engineering to standardize and streamline the entire machine learning lifecycle, from experimentation and development to deployment and maintenance. Key principles of MLOps: automation, automating model training, testing, deployment, and monitoring. Reproducibility, ensuring that models and their results can be consistently reproduced. Version control, managing code, data, and models in a version manner. Continuous integration/continuous delivery, CI/CD, applying software engineering CI/CD principles to machine learning pipelines, allowing for frequent and reliable model updates. Monitoring and alerting, proactive tracking of model and infrastructure performance. Common tools and platforms supporting MLOps include Docker for containerization, Kubernetes for container orchestration, Apache Airflow for workflow management, and cloud-specific ML platforms like AWS SageMaker, Azure Machine Learning, and Google Cloud AI Platform. These tools provide the infrastructure and services needed to build robust and scalable model deployment pipelines. Conceptual deployment architecture. A typical conceptual architecture for deploying a forecasting model might look like this. Download the code on one Pagecode Substack. In this flow, 1. Data sources provide the input data required for forecasting. 2. Data ingestion/pre-processing pipelines clean, transform, and prepare this data for the model. 3. The prediction service, your deployed model, consumes the prepared data and generates forecasts. This could be an API endpoint for real-time requests or a scheduled batch script. 4. The forecasts are then consumed by a reporting, dashboard, or application layer, making them accessible to end users or OT. Her systems. 5. For external access, an API gateway/load balancer manages incoming requests, routes them to the correct prediction service instance, and handles security. 6. A monitoring and alerting system continuously tracks the health and performance of the entire pipeline, ensuring the model remains accurate and operational. Deploying to production is a critical milestone that brings your forecasting model to life, enabling it to deliver continuous value. It transitions the model from an analytical artifact to an integral, automated component of a larger system, laying the groundwork for ongoing monitoring and continuous improvement. Monitoring. Once a time series forecasting model has been developed, rigorously tested, and deployed into a production environment, the journey is far from over. In fact, a critical and continuous phase begins. Monitoring. Monitoring a deployed forecasting model is essential to ensure its continued accuracy, reliability, and value in real-world scenarios. Without robust monitoring, even the most sophisticated model can silently degrade in performance, leading to poor decision-making and potentially significant business losses. The necessity of continuous monitoring. The core purpose of monitoring is to assess how well the model's forecasts align with the actual observed values over time. Unlike a static analytical report, a deployed model operates in a dynamic environment where underlying patterns can shift, external factors can intervene, and data quality issues can emerge. Monitoring acts as an early warning system, allowing practitioners to detect deviations, diagnose root causes, and take corrective actions before problems escalate. Consider a model forecasting daily temperature for an outdoor event planner. Initially, it might perform exceptionally well. However, an unexpected heat wave, a sudden cold snap, or even a change in sensor calibration could cause the model's predictions to become wildly inaccurate. Without monitoring, the planner might only realize the issue after critical decisions, like staffing or inventory, have been made based on flawed forecasts. EFAing forecast quality. Key metrics. To systematically compare forecasts to actuals and quantify performance degradation, we rely on a set of statistical metrics. These metrics provide objective measures of error and bias, allowing for consistent evaluation over time. While many metrics exist, some are particularly common in time series forecasting. Mean absolute error, MA the average of the absolute differences between forecasts and actual values. MIThy is easy to interpret as it's in the same units as the data, but it treats all errors equally. Mean squared error, MSE, / root means squared error. RMSE calculates the average of the square differences, penalizing larger errors more heavily. RMSE is the square root of MSE, bringing the error back into the same units as the data, making it more interpretable than MSE itself. RMSE is sensitive to outliers. Mean absolute percentage error. MAPE expresses the error as a percentage of the actual value. This is useful for comparing performance across different datasets or series with varying scales, but can be problematic with zero or near zero actual values. Bias. Mean error the average of the differences between forecasts and actual values, without taking absolute values. A positive bias indicates the model generally overpredicts, while a negative bias indicates underprediction. Bias helps identify systematic errors. Let's illustrate how to calculate these common metrics using Python. For this, we'll simulate. See some actual and forecasted values. Download the code on one Pagecode Substack. This initial code block sets up a simple dataset for demonstration. We generate 100 daily data points, simulating code snippet time series values with a trend and seasonality, and code snippet values that are generally close to the actuals, but include some random noise to represent prediction error. This data frame will serve as our basis for calculating various error metrics. Calculating key error metrics. Now, let's calculate MAE, RMSE, MAPE, and bias using our simulated data. Download the code on one Pagecode Substack. Here, we compute MAE and RMSE. Code snippet and code snippet from code snippet are convenient for this. MAE gives us the average magnitude of errors, while RMSE, by squaring errors, penalizes larger errors more, making it sensitive to outliers. Both are in the same units as our original data, making them directly interpretable. Download the code on one Pagecode Substack. MAPE is particularly useful for communicating forecast accuracy in a percentage format, which is often more intuitive for business stakeholders. However, it's crucial to handle cases where actual values are zero or very close to zero, as this can lead to division by zero or extremely large, misleading percentage errors. Our custom function includes a basic filter for non-zero actuals. Download the code on one Pagecode Substack. Bias provides insight into whether the model systematically overpredicts or under-PR. Edicts. A positive bias indicates overprediction on average, while a negative bias indicates underprediction. This metric is crucial for understanding the directional tendency of the forecast errors, which might require different corrective actions than simply reducing overall error magnitude. Visualizing performance over time. While numerical metrics provide a summary, visualizing actuals versus forecasts and the errors themselves is indispensable for understanding model behavior and diagnosing issues. Visualizations can quickly reveal trends and errors, periods of poor performance, and the impact of specific events. Download the code on one Pagecode Substack. This plot is the most fundamental visualization for monitoring. By visually comparing the code snippet line to the code snippet line, we can immediately spot periods where the model deviates significantly or consistently. For instance, if the red dashed line consistently runs above the blue line, it suggests an over-forecasting bias. If the lines suddenly diverge sharply at a specific point, it might indicate an external shock or data issue. Download the code on one Pagecode Substack. Plotting the code snippet, residuals, directly helps in identifying patterns in the errors themselves. Ideally, errors should be randomly distributed around zero. Trends, e.g., errors consistently increasing or decreasing. Seasonality in errors or sudden spikes indicate underlying problems with the model or the data. For example, a sustained positive error indicates consistent overprediction. Understanding and diagnosing forecast degradation. When monitoring reveals a decline in model performance, the next crucial step is to diagnose the root cause. Degradation can stem from several factors, often categorized into 1. Data drift. Data drift refers to changes in the distribution of the input data features that the model receives. The world evolves, and the characteristics of the data used for forecasting can shift. For example, if a sales forecasting model was trained on data where most transactions occurred on weekdays, but a new policy shifts a significant portion of sales to weekends, the input distribution has drifted. The model might not be well equipped to handle these new patterns. 2. Concept drift. Concept drift occurs when the underlying relationship between the input features and the target variable changes over time. The concept the model learned during training is no longer valid. For instance, a model predicting housing prices might learn that square footage is the primary driver. However, if a new urban development suddenly makes proximity to public transport a much stronger factor, the concept has drifted. The old relationship, square footage dash price, is less accurate, even if the square footage distribution hasn't changed. 3. External shocks and anomalies. These are sudden, often unpredictable events that significantly impact the time series, making historical patterns irrelevant or misleading for a period. Examples include economic downturns or booms. A recession can drastically alter consumer spending habits. Policy changes, new regulations, e.g., tariffs, environmental laws, can affect supply chains or demand. Natural disasters, hurricanes, floods, or pandemics can disrupt normal operations and demand patterns. Technical failures, sensor malfunctions, data pipeline breaks, or system outages can introduce erroneous or missing data. Major competitor actions. A new product launch or pricing strategy from a competitor can shift market dynamics. Social events. Major holidays, sporting events, or cultural shifts can temporarily or permanently alter behavior. It's important to distinguish between temporary performance dips due to anomalies and sustained degradation requiring intervention. A single outlier might be an anomaly, while a consistent increase in error over weeks suggests drift. 4. Model staleness. Sometimes, a model simply becomes stale because the world generally evolves, and the patterns it learned from historical data slowly become less representative of current reality. This is a more gradual form of concept drift, not tied to a single identifiable event, but rather a continuous shift. Regular retraining or adaptive models can address staleness. Automated monitoring and alerting. Manual inspection of charts and metrics is unsustainable for continuous monitoring, especially with many models. Automated monitoring systems are crucial. These systems can calculate metrics periodically, daily, hourly, or even more frequently. Compare current performance to historical benchmarks. Is the current RMSE significantly worse than the average RMSE over the last month? Trigger alerts. Send notifications, email, Slack, PagerDuty if a metric crosses a predefined threshold or if data drift is detected. Generate dashboards. Provide a consolidated view of model health and performance. Let's look at a simplified example of setting up a basic automated check and alert. Download the code on OnePageCode Substack. This code snippet demonstrates a basic automated check. We simulate a period of degraded performance within our dataset. The code snippet function calculates the current RMSE and compares it against a predefined code snippet. If the RMSE exceeds this threshold, an alert message is printed in a real system. This would trigger an actual notification. This simple mechanism can be scheduled to run periodically, providing continuous oversight. Actionable steps when monitoring reveals issues. Detecting a problem is only the first step. The true value of monitoring lies in enabling timely and effective responses. 1. Investigate and diagnose. Use visualizations and deeper analysis, e.g., examining specific features, looking for external event correlations to pinpoint the exact cause of degradation, data drift, concept drift, external shock. 2. Retrain the model. If the underlying data patterns have shifted significantly, data or concept drift, retraining the model on more recent, representative data is often the most effective solution. This might involve including the new, changed data in the training set. 3. Model updates and feature engineering. If the existing model architecture is no longer suitable, or if new influential features have emerged, the model might need a more substantial update. This could involve trying different algorithms, adjusting hyperparameters, or incorporating new data sources. 4. Data quality checks. Sometimes performance degradation is simply due to issues in the data pipeline, missing values, incorrect units, or corrupted data. Monitoring input data quality is as important as monitoring model output. 5. Reevaluate assumptions. The initial assumptions made during model development, e.g., about seasonality, trends, or external influences, might no longer hold true. A reevaluation can lead to fundamental changes in the forecasting approach. 6. Temporary intervention. For temporary external shocks, a short-term manual override or a simpler, more robust model might be deployed until the system returns to normal. Tools and technologies for operational monitoring. While our code examples use basic Python libraries, in a production environment, specialized tools and platforms are often employed for robust ML model monitoring. MLOps platforms, tools like MLflow, AWS SageMaker, Azure ML, Google Cloud AI Platform, and Kubeflow offer integrated capabilities or model deployment, monitoring, and retraining pipelines. Observability tools, solutions like Grafana, Prometheus, Datadog, and custom dashboards built with tools like Tableau or Power BI can visualize metrics, logs, and alerts from your forecasting systems. Data drift detection libraries. Libraries like Evidently AI, NannyML, and Fiddler AI are specifically designed to detect data and concept drift, often integrating with MLOps platforms. Alerting systems, PagerDuty, OpsGenie, or even simple integrations with Slack/email for critical alerts. Monitoring is not a one-time task, but an ongoing commitment. It closes the loop in the time series forecasting lifecycle, ensuring that models continue to provide accurate and valuable insights long after their initial deployment. Collecting new data, the engine of continuous forecasting. In the dynamic landscape of real-world applications, a forecasting model is rarely a static entity. Once deployed to production and under constant monitoring, it eventually requires new data to maintain its accuracy and relevance. This continuous collection of new data forms a crucial feedback loop in the forecasting project roadmap, ensuring that models remain adaptive and performant in the face of changing conditions. The iterative forecasting lifecycle. The forecasting process is not a linear path, but an iterative cycle. After a model is developed, deployed, and monitored, the insights gained from monitoring, e.g., declining performance, detected data shifts, feed directly back into the data collection phase. This initiates a new cycle of model retraining and redeployment, creating a robust, self-improving system. This continuous feedback loop is fundamental to maintaining high-quality forecasts over time. Why continuous data collection is essential. The necessity of continuously collecting new data stems from several critical factors that impact a model's long-term viability. Addressing model staleness. Forecasts are based on historical patterns. As time progresses, the history on which a model was trained becomes less representative of the current reality. Without fresh data, a model becomes stale, leading to increasingly inaccurate predictions. Imagine a retail demand forecasting model trained on pre-Day. Mike sales data trying to predict post-pandemic demand. Its accuracy would severely degrade without new data reflecting the shift in consumer behavior. Adapting to evolving patterns, economic conditions, consumer preferences, technological advancements, and even seasonal patterns can subtly or dramatically shift over time. New data captures these evolving trends, allowing the model to learn and adapt its internal representations. For instance, a model predicting energy consumption must adapt to the increasing adoption of renewable energy sources or changes in appliance efficiency standards. The concept of data drift and model drift. These are perhaps the most compelling reasons for continuous data collection and retraining. Data drift occurs when the statistical properties of the input data, features, or the relationship between inputs and outputs, target variable, change over time. Covariate shift. The distribution of the input features changes. For example, if a model predicts stock prices based on trading volume, and suddenly the average daily trading volume significantly increases across the market, the model might struggle because the input distribution has shifted. Concept drift. The relationship between the input features and the target variable changes. For example, in a fraud detection model, the patterns of fraudulent transactions might evolve as fraudsters find new ways to exploit systems, meaning the concept of fraud itself has changed. Model drift. A direct consequence of data drift. As the underlying data distribution changes, the model's learned patterns, its concepts, no longer accurately reflect the current reality, leading to a decline in its predictive performance. Continuous data collection and retraining are the primary mechanisms to counteract both data and model drift. Methods and tools for automated data collection. In a production environment, manual data collection is impractical and prone to errors. Automation is key. Here are common methods and tools. Database integrations. Many applications store their operational data in relational databases, e.g., PostgreSQL, MySQL, SQL Server, or NoSQL databases, e.g., MongoDB, Cassandra. Automated scripts, or ETL, extract, transform, load, pipelines can regularly query these databases to pull new transactional data, sensor readings, or user interactions. APIs, application programming interfaces for external data sources, weather data, stock prices, social media trends, competitor pricing. APIs provide a programmatic way to fetch data. Scheduled jobs can call these APIs to retrieve the latest information. Streaming data platforms. For high-velocity, real-time data, platforms like Apache Kafka, Amazon Kinesis, or Google Cloud Pub/Sub are used. These systems allow data to be continuously ingested and processed as it arrives, making it available for near real-time forecasting or immediate appending to historical datasets. Web scraping, while less robust and more prone to breakage, web scraping can be used to collect data from websites that do not offer an API. This typically involves using libraries like CodeSnippet or CodeSnippet to parse HTML content. Flat files and cloud storage. Data might arrive in structured flat files, CSV, per K, uploaded to cloud storage buckets, e.g., AWS S3, Google Cloud Storage, Azure Blob Storage. Automated processes can monitor these locations and ingest new files. Triggers for new data collection and retraining. Deciding when to collect new data and retrain a model is crucial. Common triggers include scheduled intervals, the simplest approach. Models might be retrained daily, weekly, monthly, or quarterly, depending on the data's volatility and the business's needs. This provides a predictable cadence for updates. Performance degradation thresholds. Monitoring systems can track key performance metrics, e.g., RMSC, ND, R-squared. If a metric falls below a predefined threshold, it can trigger an alert and initiate a retraining process. Detection of data drift. Advanced monitoring tools can analyze incoming data stream for shifts in statistical properties, e.g., mean, variance, distribution shape, or changes in feature importance. When significant drift is detected, it signals the need for retraining. External events/business triggers. Specific business events can necessitate retraining. For example, a major marketing campaign, the launch of a new product line, a significant policy hang, or an unforeseen global event, like a pandemic, might require immediate model updates. Practical demonstration. Simulating new data arrival and appending. To illustrate the concept of new data collection and appending, let's simulate a time series dataset representing daily sales. We'll start with an initial dataset and then simulate new data arriving daily, appending it to our existing records. First, we'll create a synthetic initial dataset using CodeSnippet. Download the code, on one patch code Substack. This initial code block sets up our baseline dataset, simulating daily sales for January 2023. We create a code snippet with a code snippet index and a code snippet column, representing the historical data our model would have been trained on. Now, let's simulate new data arriving for a few days in February and append it to our existing dataset. Download the code on one patch code Substack. This second chunk generates a small batch of new sales data, simulating what might arrive from a daily data feed. Notice that we've intentionally varied the base sales and noise slightly to mimic real-world fluctuations. Finally, we append this new data to our code snippet, demonstrating the continuous data collection process. Download the code on one patch code Substack. The code snippet function is a common and efficient way to append new time series data. After this operation, code snippet now contains both the original January data and the newly collected February data, REA. DY for potential retraining. In a real system, this combined dataset might then be saved back to a data warehouse or used directly by a retraining pipeline. Managing model versions. Once a model is retrained with new data, it becomes a new version of the model. Effective version management is critical in a production environment. Reproducibility. Being able to revert to previous model versions if a new one performs poorly is essential. Auditability. Tracking which data was used to train which model version and when is vital for debugging and compliance. A/B testing. New model versions can be tested against older ones in a live environment to confirm performance improvements before full rollout. Tools like MLflow, DVC, Data Version Control, or dedicated MLOps platforms provide functionalities for tracking model artifacts, parameters, and performance metrics across different versions. Computational resources and trade-offs. Continuous retraining is not without its costs and complexities. Infrastructure requirements. Retraining models, especially complex deep learning models on large datasets, requires significant computational resources, CPUs, GPUs, memory. This necessitates robust cloud infrastructure or on-premise compute clusters. Cost. The computational resources translate directly into operational costs. Cloud providers charge for compute time, storage, and data transfer. Complexity. Building automated data pipelines, retraining triggers, model versioning SY. Stems and CI/CD, continuous integration / continuous deployment. Pipelines add significant engineering overhead. Latency. The time it takes to retrain and redeploy a model can vary from minutes to hours. For very fast-changing environments, this latency might still be too high. Trade-offs. The decision on retraining frequency involves a trade-off between model accuracy. More frequent retraining generally means higher accuracy and cost/complexity. A business must evaluate the value of increased accuracy against the resources required. For some applications, weekly retraining might be sufficient, while others might demand daily or even hourly updates. Addressing cold start problems. A cold start problem occurs when there is insufficient historical data to train a robust model, often for new products, services, or locations. When collecting new data for a new series, strategies include proxy data, using data from similar existing products or services as a proxy until enough specific data accumulates. Rule-based models, starting with simple, expert-defined rules or statistical averages until data allows for more sophisticated models. Transfer learning, if applicable, using a pre-trained model from a related domain and fine-tuning it with the limited new data. Hierarchical forecasting. If a new series is part of a larger hierarchy, forecasting at a higher aggregate level and disaggregating. Real-world applications. The continuous collection of new data and subsequent T-model retraining is critical across numerous industries. Retail demand forecasting, daily sales data, promotional impacts, and even weather patterns are continuously collected to refine predictions for inventory management, staffing, and marketing campaigns. Energy consumption prediction, real-time sensor data from smart grids, Weather forecasts and historical consumption patterns are fed into models to optimize power generation and distribution. Financial market prediction. High-frequency trading models continuously ingest new tick data, new sentiment, and economic indicators to adapt to rapidly changing market conditions. Fraud detection. New transaction data, evolving fraud patterns, and user behavior logs are constantly collected to update models that identify suspicious activities. As fraudsters adapt, the models must too. Healthcare outcome prediction. Patient vital signs, treatment responses, and epidemiological data are continuously collected to improve models for disease progression, patient risk assessment, and resource allocation. How time series forecasting is different from other regression tasks. While time series forecasting might superficially resemble standard regression problems, its fundamental nature introduces unique challenges and necessitates specialized approaches. The core distinction lies in the inherent temporal structure and dependencies within time series data, which violate assumptions commonly made in traditional regression. Temporal dependence, the core distinction. In most standard regression tasks, a critical assumption is that observations are independent and identically distributed, i.d. This means that each data point is drawn independently from the same underlying distribution. For example, when predicting house prices, the price of one house is generally assumed not to directly depend on the price of a house sold a month ago in a different neighborhood, beyond shared market conditions captured by features. Time series data, however, inherently violates this IID assumption. The value of a variable at a given time point is often highly dependent on its past values and the values of other variables at preceding time points. This characteristic is known as temporal dependence or autocorrelation. Consider predicting tomorrow's temperature. It's highly probable that tomorrow's temperature will be very close to today's, or at least influenced by it, rather than being an entirely random draw from a distribution of all possible temperatures. This direct link to the past is what defines time series data and sets it apart. Key characteristics of time series data. Beyond temporal dependence, several other characteristics distinguish time series forecasting. Autocorrelation. Autocorrelation is a specific type of temporal dependence where a variable's current value is correlated with its own past values. For instance, if you observe high electricity consumption on a weekday, it's likely that consumption on the following weekday will also be relatively high, exhibiting a daily or weekly pattern. Positive autocorrelation. High values are followed by high values and low values by low values, e.g., stock prices often trend. Negative autocorrelation. High values are followed by low values, and vice versa, less common in natural phenomena, but can occur in some oscillating systems. Ignoring significant autocorrelation can lead to models that underestimate uncertainty, produce biased forecasts, or identify spurious relationships. Stationarity. Many traditional time series models, like ARIMA, assume that the underlying statistical properties of the series, such as its mean, variance, and autocorrelation structure, remain constant over time. This property is known as stationarity. Strict stationarity. The joint probability distribution of any set of observations does not change over time. Weak sense stationarity, or covariance stationarity, the mean, variance, and autocorrelation function are constant over time. Real-world time series data is often non-stationary. Trends, e.g., increasing population over time, seasonality, e.g., higher retail sales in December, and changing variance, e.g., increased stock market volatility during crises, are common causes of non-stationarity. Handling non-stationarity, often through differencing or transformation, is a crucial step in many time series analysis pipelines. Nature of features. In standard regression, features are typically static attributes of an observation, e.g., square footage, number of bedrooms for a house. In time series forecasting, features often include lag values, past values of the target variable itself, e.g., code snippet. These directly capture autocorrelation. Time-based features, components derived from the timestamp, e.g., code snippet, code snippet. These help capture seasonality and periodic patterns. Rolling statistics, aggregations over a past window, e.g., code snippet, code snippet. These provide smoothed or summary information about recent history. These features are explicitly designed to leverage the temporal structure of the data. Implications for modeling and validation. The unique characteristics of time series data have profound implications for how we build and evaluate forecasting models. Model selection. Traditional regression models like linear regression, decision trees, or random forests, when applied naively to time series, may struggle because they are not designed to explicitly handle temporal dependencies. While they can be adapted by adding lag features, specialized time series models are often more effective. ARIMA, autoregressive integrated moving average, explicitly models autocorrelation, trends, and seasonality. Exponential smoothing, ETS models trends and seasonality using weighted averages of past observations. Profit, a robust model for business forecasting, handling trends, multiple seasonality, and holidays. Recurrent neural networks, RNNs, like LSTMs and GRUs, designed to process sequences and capture long-term dependencies. Validation strategies. The IID assumption in standard cross-validation, e.g., k-fold cross-validation, is violated in time series. Randomly splitting time series data into training and test sets can lead to 1. Data leakage. Future information might inadvertently be used to train the model, leading to overly optimistic performance estimates. For example, if a random split places a future observation into the training set, the model effectively sees the future. 2. Unrealistic evaluation. A model trained on a random mix of past and future data will not accurately reflect its performance on truly unseen future data, which is the goal of forecasting. To counter these issues, specialized time series validation strategies are crucial. Walk-forward validation, or time series cross-validation, this is the most common and robust method. The data is split chronologically. The mode. L is trained on an initial segment of data, e.g., first 70%, and evaluated on the immediately following period. Then, the training window slides forward, often by adding the evaluated period to the training set, and the model is retrained and evaluated on the next future period. This simulates how a model would be used in a real-world production environment, always forecasting into the truly unseen future. Download the code on one patch code Substack. Common pitfalls. Ignoring the temporal nature of data can lead to spurious correlations. A trend in one series might coincidentally align with a trend in another, leading to a false conclusion of causality if temporal order is ignored. Inflated performance metrics, standard R-squared or RMSE calculated on randomly split time series data, can be misleadingly high, as the model might be memorizing future patterns due to data leakage. Poor generalization. A model that performs well on a non-chronological split might fail catastrophically when deployed to forecast actual future data. Illustrative example. When standard regression fails on time series. Let's demonstrate how a simple linear regression model, applied without considering temporal order, might perform poorly or misleadingly on time series data. We'll generate a synthetic time series with a clear trend and seasonality. First, we'll set up our environment and generate some synthetic data. Download the code on one patch code Substack. We import necessary libraries. C. Code snippet for numerical operations, code snippet for data handling, code snippet for plotting, code snippet from scikit-learn for our simple model, and code snippet for evaluation. We also import code snippet to explicitly show a problematic non-temporal split. Now, let's create a synthetic time series dataset with a trend and seasonality. Download the code on one patch code Substack. Here, we generate 3 years of daily data. We define a simple linear code snippet, a sinusoidal code snippet component to simulate yearly cycles, and some random code snippet. These are combined to create our code snippet. The data is then stored in a pandas data frame with a code snippet index. This setup clearly shows temporal patterns. Let's visualize our synthetic time series to confirm its characteristics. Download the code on one patch code Substack. The plot will clearly show an upward trend and a repeating seasonal pattern, making it evident that the data points are not independent. Problematic approach, standard regression, ignoring time. We'll now treat this as a standard regression problem, where we try to predict code snippet based on a simple numerical representation of time, e.g., day number. We'll use a random train test split, mimicking how one might apply standard regression without considering time series specific validation. Download the code on one patch code Substack. We create a new feature code snippet, which is the number of days since the start of the series. This allows us to use a numerical feature in our regression model. Code snippet will be our feature matrix, and code snippet our target. Now, we'll perform a random train test split. This is the problematic step for time series data. Download the code on one patch code Substack. Notice how code snippet shuffles the data by default before splitting, meaning code snippet will contain data points from various points in time, potentially including data before some points in code snippet or after others. This mixes future and past information. Next, we train a simple linear regression model on this randomly split data. Download the code on one patch code Substack. The code snippet model fits a straight line to the relationship between code snippet and code snippet. While the RMSE might seem reasonable, this model fundamentally ignores the seasonality and treats all errors as independent, which they are not. The random split means the test set contains future and past points relative to each other, making the evaluation metric less meaningful for forecasting. Conceptual better approach, time-aware split. For a true time series problem, we must maintain the temporal order in our splits. This means training on an earlier period and testing on a later, truly unseen period. Download the code on one patch code Substack. Here, code snippet and code snippet contain data from the earliest dates up to the code snippet, and code snippet contain all data from code snippet onwards. This ensures the test set is entirely in the future relative to the training set. Now, we train the same code snippet model on this time-aware split. Download the code on one patch code Substack. The RMSE here will likely be higher than the one from the random split, reflecting the model's inability to capture the seasonality or complex nonlinear trends when only given code snippet as a feature and evaluated on truly unseen future data. The linear model simply extends the observed trend, failing to capture the seasonal fluctuations. Finally, let's visualize the predictions from the time-aware split. Download the code on one patch code Substack. The plot clearly shows the linear regression model failing to capture the seasonality in the test set. It merely extends the linear trend it learned from the training data. This illustrates why specialized time series methods, or at least more sophisticated feature engineering, e.g., adding sine/cosine features for seasonality or lag values, are necessary. This simple example highlights that while linear regression is a valid regression technique, its naive application to time series data, without accounting for temporal dependencies and proper validation, can lead to significantly flawed forecasts and misleading performance evaluations. Time series forecasting demands a deeper understanding of data characteristics and tailored methodologies. The inherent order of time series data. One of the most fundamental distinctions between time series forecasting and other common regression tasks lies in the inherent order of the data. Unlike many datasets where the sequence of observations is arbitrary, time series data possesses a crucial chronological dependency. Each data point is linked to the one before it and influences the one after it. Consider a typical regression problem, such as predicting house prices based on features like square footage, number of bedrooms, and location. In such a scenario, the order in which you receive the data points, individual house sales, typically doesn't matter. You could randomly shuffle the entire data set, and a regression model would still learn the underlying relationships between features and price effectively. The model seeks to understand static correlations rather than temporal dynamics. In contrast, a time series, such as daily stock prices, hourly electricity consumption, or monthly sales figures, is defined by its sequential nature. The value of electricity consumption at 3 p.m. is directly related to the consumption at 2 p.m., and it impacts the consumption at 4 p.m. This temporal dependence means that future values are often a function of past values, and the order of observations is critical for understanding these relationships. This inherent order has profound implications for how we prepare, analyze, and model time series data. In Python, time series are frequently handled. Using the pandas library, which provides powerful tools like the code snippet to explicitly manage and leverage this temporal order. Download the code on one Code Substack. In this conceptual example, code snippet represents observations collected over time. Notice the code snippet. This index ensures that the data maintains its chronological order, which is fundamental for any time series operation. If we were to randomly shuffle the rows of this data frame, we would destroy the temporal relationships that are vital for forecasting. Now, let's look at a conceptual non-time series dataset for comparison. Download the code on one Code Substack. For code snippet, each row represents an independent observation. Shuffling these rows would not alter the underlying statistical relationships between code snippet, and code snippet. This distinction is paramount when deciding how to split data for model training and evaluation. The criticality of chronological data splitting. Because time series data has a temporal order, the way we split it into training and testing sets must respect this order. This is a crucial difference from standard regression tasks, where random splitting is commonplace and often preferred to ensure representativeness across the dataset. Why random shuffling is forbidden. In a standard regression problem, you might use a function like code snippet with code snippet to randomly partition your data. This is done to ensure that both the training and testing sets are representative of the overall data distribution and to prevent any implicit ordering from affecting the model. Download the code on one Code Substack. In this scenario, code snippet and code snippet contain data points from across the entire original dataset, mixed randomly. This approach is perfectly valid when the order of observations does not carry predictive information. However, applying this random shuffling to time series data would be a critical error, leading to a phenomenon known as look-ahead bias, also called data leakage or future leakage. Introducing look-ahead bias, data leakage. Look-ahead bias occurs when information from the future leaks into the past, specifically into the training set. If you randomly shuffle and split a time series, there's a high probability that your training set will contain data points that occurred after some of the data points in your test set. Imagine you're trying to predict tomorrow's stock price. If your training data includes stock prices from next week, your model would have access to future information. While this might make your model appear highly accurate during development, its performance would drastically degrade in a real-world scenario where future information is, by definition, unavailable. The model is effectively cheating by seeing the answers before the test. Correct versus incorrect train test splits for time series. To avoid look-ahead bias, time series data must always be split chronologically. This means that your training set consists of data up to a certain point in time, and your test set consists of data strictly after that point. Incorrect split, random shuffling. Download the code on one Code Substack. The commented out code above illustrates a common pitfall. If executed, code snippet and code snippet would contain a mix of dates from the entire period, making it impossible to simulate real-world forecasting where only past data is available. Correct split, chronological. The correct approach involves defining a cutoff date or a specific percentage of the earliest data for training and the remaining, most recent data for testing. Download the code on one Code Substack. In this correct split, code snippet contains observations only up to a certain date, and code snippet contains observations strictly after that date. This setup accurately simulates a real-world forecasting scenario where you train your model on historical data and then use it to predict future, unseen values. Consequences of look-ahead bias. The practical consequences of look-ahead bias are severe. 1. Artificially inflated performance metrics. Your model will show excellent performance metrics, e.g., low mean absolute error, high R-squared, during development and cross-validation because it has inadvertently seen future information. 2. Failure in real-world deployment. When you deploy such a model into production, it will encounter truly unseen future data, and its performance will likely be significantly worse than what was observed during development. This can lead to incorrect business decisions, financial losses, or operational inefficiencies. 3. Misleading model selection. You might select a complex model that appears to perform well due to leakage, when a simpler, more robust model would have been more appropriate and effective without the bias. Understanding look-ahead bias in detail. Look-ahead bias is a critical pitfall in time series analysis. It undermines the validity of your model's performance evaluation and, consequently, its real-world utility. Formally, look-ahead bias occurs whenever information that would not be available at the time of a real-world prediction is used during the model's training or evaluation phase. This can happen in several ways beyond just incorrect train test splits. Using future-derived features. If you create a feature for a model, e.g., a moving average, that inadvertently includes data points from the future relative to the prediction point. For instance, calculating a 5-day moving average for today's prediction using tomorrow's data. Improper data imputation. Filling missing values in a time series using methods that consider future observations, e.g., forward filling from the end of the series, or using a global mean/median calculated over the entire series, including future data. Incorrect cross-validation. Applying standard k-fold cross-validation, which shuffles data, time series data, instead of time series-specific methods like code snippet. Illustrative example. Predicting temperature. Let's consider a simple, concrete example to highlight look-ahead bias. Suppose we want to predict today's maximum temperature. Scenario 1. No look-ahead bias correct. To predict today's maximum temperature, we can use yesterday's maximum temperature, the average temperature of the past 7 days, ending yesterday, today's humidity, if known before temperature peaks, historical patterns for this date. All the information used is from the past or is concurrently available. Scenario 2. Look-ahead bias present, incorrect. To predict today's maximum temperature, we mistakenly use tomorrow's maximum temperature or an average that includes it, the average temperature of the next 7 days. The overall average maximum temperature for the entire year, calculated after the year has ended. If our model is trained using any of the mistaken features, it will appear to perform exceptionally well because it's effectively predicting today's temperature by peeking at tomorrow's or future information. Download the code on OnePageCode Substack. In the incorrect approach, if our model learns that code snippet is often close to code snippet, and we feed code snippet as a feature for code snippet, the model will look incredibly accurate. However, in a real-world setting on day 1, code snippet is unknown, rendering the model useless. Real-world impact on model deployment. The consequences of ignoring time series order and allowing look-ahead bias to creep into your models can be severe in real-world applications. Financial trading. A trading algorithm built with look-ahead bias might show incredible paper profits during backtesting, only to incur significant losses when deployed with real money, as it no longer has access to future price movements. Demand forecasting. A retail chain using a demand forecasting model with look-ahead bias might consistently overstock or understock, leading to wasted inventory or lost sales, because the model's accuracy was based on knowing future sales trends. Energy consumption prediction. An energy grid operator relying on a biased consumption forecast could mismanage power generation, leading to blackouts or unnecessary energy production costs. Understanding and meticulously avoiding look-ahead bias is not just a theoretical exercise. It is a fundamental best practice for building robust, reliable, and deployable time series forecasting models. It ensures that the model's performance observed during development is a true reflection of its capabilities in an operational environment. 1.3.2 time series sometimes do not have features. One of the most striking differences between time series forecasting and other common regression tasks lies in the nature of the input data, specifically regarding features or independent variables. In many traditional regression problems, you aim to predict a target variable based on a set of distinct, often independent, predictor variables. For example, predicting house prices, target, might involve features like square footage, number of bedrooms, and location. However, in time series forecasting, it's very common and often sufficient to predict future values of a series using only its own past values. This means the time series itself becomes its own source of predictive features. How past values become features, the concept of lags. When we say a time series can be forecasted without external features, we mean that the historical observations of the series itself provide the necessary information. These past observations are often referred to as lag values. Consider a daily temperature series. To predict tomorrow's temperature, you might find that yesterday's temperature, or the temperature from a week ago, is a highly effective predictor. In this scenario, the target variable is code snippet, temperature at time code snippet. The features are code snippet, temperature at time code snippet, a 1-day lag, code snippet, temperature at time code snippet, a 7-day lag, and so on. This approach leverages the inherent autocorrelation within a time series, which is the correlation of a series with its own past values. If a series exhibits strong autocorrelation, its past values contain significant information about its future. Why time series often lack external features? There are several practical reasons why time series forecasting models often rely solely on the series' own history. 1. Data availability and cost. Collecting reliable external features can be challenging, expensive, or even impossible. For instance, if you're forecasting the number of daily calls to a customer service center, obtaining precise, real-time data on all potential external factors, e.g., specific product defects, competitor promotions, social media sentiment, might be impractical or too costly. 2. Privacy and regulations. In some domains, external data might be subject to strict privacy regulations or proprietary restrictions, making it inaccessible for modeling. 3. Sufficiency of internal information. For many time series, the underlying dynamics and trends are primarily driven by their own historical progression. The momentum or cyclical patterns within the series might be strong enough that external factors offer only marginal additional predictive power, especially for short-term forecasts. 4. Simplicity and interpretability. Models that rely only on the series' own past values, univariate models, are often simpler to build, train, and interpret, which can be advantageous in production environments. Implications for modeling approaches. This characteristic, the ability to forecast using only historical values, leads directly to a class of powerful and widely used time series models known as univariate time series models. These models are designed specifically to exploit the internal structure of a single time series without requiring additional exogenous, external variables. Autoregressive AR models. These models explicitly use past values of the time series itself as predictors for future values. For example, an AR1 model predicts the current value based on the immediately preceding value, much like the temperature example above. Moving average MA models. While less intuitive at first glance, MA models use past forecast errors, which are derived from the series history, to predict current values. This also means they rely entirely on the historical behavior of the series. Both AR and MA models, along with their combinations like ARIMA models, are foundational in time series analysis precisely because they leverage the self-referential nature of time series data. They stand in contrast to multivariate regression models, which inherently require multiple independent feature inputs. Real-world examples. Consider these common forecasting scenarios where models frequently rely solely on the target series past. Daily website visits. Predicting the number of visitors to a website tomorrow often uses only the historical daily visit counts, while marketing campaigns or news events might influence visits, A baseline forecast can often be achieved by understanding daily, weekly, and seasonal patterns inherent in past visits. Monthly electricity consumption. Utility companies often forecast future electricity demand based predominantly on historical consumption patterns, accounting for seasonality, e.g., higher in summer/winter, and long-term trends. While temperature is a strong external factor, a basic forecast can still capture much of the variation from historical consumption alone. Specific product sales. Univariate view forecasting the sales of a particular product where detailed marketing spend or competitor data is unavailable. The model might rely on previous daily or weekly sales figures, looking for trends, seasonality, e.g., holiday spikes, or cyclical patterns. In these cases, the historical sequence of the variable itself provides a rich source of information, allowing for effective forecasting even in the absence of external features. This fundamental distinction underscores why time series forecasting requires a different analytical toolkit and mindset compared to traditional regression problems. Summary: consolidating foundational time series concepts. This section consolidates the foundational concepts introduced in the preceding chapters, reinforcing your understanding of what time series data is, its unique characteristics, and the high-level roadmap for successful forecasting projects. Mastering these core ideas is essential before diving into the practical implementation and advanced modeling techniques covered in later sections of this book. What is a time series? At its core, a time series is a sequence of data points indexed or listed in time order. This means that each observation in the dataset is associated with a specific timestamp, and the order of these observations is paramount. Unlike typical regression problems where observations are often considered independent and identically distributed, i.d., the chronological dependency between data points is the defining characteristic of time series. Consider daily stock prices, hourly temperature readings, or monthly sales figures. In each case, the value at any given point in time is often influenced by its past values. This temporal dependency is precisely what makes time series forecasting a distinct and fascinating field. Deconstructing a time series components. Understanding the intrinsic components that make up a time series is crucial for effective analysis and model selection. Most time series can be decomposed into three primary components. Trend. The trend represents the long-term progression or direction of a series. It reflects a general increase, decrease, or stability over an extended period, abstracting from short-term fluctuations. For example, a company's sales might show an upward trend over several years, or global temperatures might exhibit an increasing trend over decades. Identifying a trend is vital because it often indicates underlying structural changes or growth patterns that need to be captured by a forecasting model. If a series has a strong upward trend, a model that only considers seasonality might consistently underpredict future values. Seasonality. Seasonality refers to repetitive, predictable patterns or cycles that occur at fixed intervals within a time series. These patterns are typically tied to calendar periods, such as daily, e.g., peak electricity usage in the evening, weekly, e.g., higher retail sales on weekends, monthly, e.g., spike in ice cream sales during summer months, or yearly, e.g., increase holiday spending in December. Recognizing seasonality is incredibly important for model choice. Many powerful time series models, such as the Seasonal Autoregressive Integrated Moving Average, SARIMA, family, are specifically designed to capture and forecast these periodic fluctuations. Ignoring seasonality can lead to significantly inaccurate predictions, especially for short-term forecasts where these patterns dominate. Residuals, NIJA. The residuals, also known as the irregular component or noise, represent the random fluctuations or unpredictable variations in the time series that remain after the trend and seasonal components have been removed. These are the unexplained variations that a model attempts to minimize. In an ideal forecasting scenario, the residuals should be purely random, with no discernible patterns or structure left. If patterns persist in the residuals, It indicates that the model has not fully captured all the systematic information in the data, suggesting that it could be improved. Analyzing residuals is a critical step in evaluating a model's performance and identifying areas for refinement. The paramount importance of data order. Perhaps the most defining characteristic that sets time series forecasting apart from other regression tasks is the absolute necessity of preserving the chronological order of the data. Unlike standard regression, where you might randomly shuffle your data before splitting it into training and testing sets, doing so with time series data would destroy the inherent temporal dependencies and render your forecast meaningless. Imagine trying to predict tomorrow's stock price by randomly selecting past prices from any date, regardless of their sequence. This would violate the fundamental principle that the future is influenced by the immediate past, not a random collection of historical points. Pitfall: random shuffling. A common pitfall for those new to time series is applying standard machine learning data splitting techniques, like to snippet without code snippet, that randomly distribute data points. This is catastrophic for time series as it leaks future information into the training set and breaks the causal relationship required for accurate forecasting. Best practice: time-based splitting. For time series, data must always be split chronologically. This means your training set consists of data up to a certain point in time, and your validation/test set consists of data after that point. This approach simulates a real-world forecasting scenario where you use historical data to predict unseen future values. Let's illustrate this with a conceptual Python example. In this book, Python will be our primary language for implementing time series concepts. Download the code on one pagecode Substack. This initial chunk creates a simple number py array to represent our time series data. In a real application, this code snippet array would typically be a column in a pandas data frame, accompanied by a datetime index. Download the code on one pagecode Substack. Here, we calculate the index where we will split our data. This index ensures that all data points before this point go into the training set, and all data points from this point onwards go into the testing set. Download the code on one pagecode Substack. This code block demonstrates the correct method for splitting time series data. The training set contains the earliest observations, and the test set contains the latest observations, maintaining the chronological order. This setup accurately reflects how a model would be used in production, trained on past data to predict future outcomes. Download the code on one pagecode Substack. This final code chunk illustrates a common mistake: using a random split. Observe that the code snippet and code snippet arrays contain a mix of early and late data points, destroying the temporal sequence. If a model were trained on code snippet, it would have seen future information, leading to overly optimistic and misleading performance metrics. This highlights why careful attention to data splitting is a critical programming practice in time series forecasting. Time series forecasting project roadmap. A successful time series forecasting project, regardless of its scale, generally follows a structured roadmap. Understanding these high-level steps helps in planning and executing your analysis effectively. 1. Define the problem and goal. Clearly articulate what you're trying to predict, why it's important, and the desired accuracy or performance metrics. Is it a short-term forecast for inventory or a long-term forecast for strategic planning? 2. Data collection and preparation. Gather the relevant time series data. This involves cleaning, handling missing values, ensuring consistent time intervals, and aligning data from multiple sources if necessary. 3. Exploratory data analysis. EDA visualize and analyze the time series to identify its components, trend, seasonality, cycles, outliers, and any structural breaks. This step directly leverages your understanding of time series components. 4. Model selection and training. Choose appropriate forecasting models based on your EDA findings and project goals. This could range from traditional statistical models, e.g., ARIMA, exponential smoothing, to more complex machine learning or deep learning models, e.g., Prophet, LSTMs, transformers. 5. Model evaluation. Assess the model's performance using appropriate metrics, e.g., RMSC, and MAPE on unseen data, your time-based test set. Ensure the model generalizes well and doesn't just memorize the training data. 6. Deployment and monitoring. Implement the model into a production environment and continuously monitor its performance. Time series characteristics can change over time, concept drift, so models often need to be retrained or updated. This roadmap provides a framework for approaching any time series challenge. Throughout this book, we will delve into each of these steps in detail, equipping you with the Python tools and techniques to execute them effectively. We will explore both traditional statistical models, which provide a strong foundation and interpretability, as well as modern machine learning and deep learning approaches, which often excel with complex, large-scale datasets.